Okay, so in this chapter, I would like to talk about mass, Bernoulli, and energy equation. Alright, wind turbine farms are being constructed all over the world to extract kinetic energy from the wind and convert it to electrical energy. The mass, energy, momentum, and angular momentum balances are utilized in the design of a wind turbine. The Bernoulli equation is also useful in the preliminary design stage. So, wind turbine is a place where the wind kinetic energy are being extracted from the wind. As you know, the wind is moving very fast in certain area of the land. So this wind energy can be converted into mechanical energy by using wind turbine. Okay, it's a mechanical device. So a lot of wind turbine combine to form a wind turbine farm. Alright, so this is a place where the energy are being extracted. So to estimate the energy that can be actually captured by the wind turbine, we can use the Bernoulli equation, and that's where it is being used in the preliminary design stage. So in this chapter, we will look into how to apply the conservation of mass equation to balance the incoming and outgoing flow rates in a flow system. And second, we will recognize various forms of mechanical energy and work with energy conversion efficiency. And third, understand the use and limitations of Bernoulli equation and apply it to solve a variety of fluid flow problem. And fourth, work with energy equation expressed in terms of head and use it to determine turbine power output and pumping power requirement. Alright, in this chapter, we will look into conservation law such as the conservations of mass, conservations of energy, and conservations of momentum. So historically, the conservation law are first applied to a fixed quantity of matter called closed system, or in other words, we call it control mass. So in this system, we do not allow the mass to enter or leave a system, but we only allow the heat or energy to enter and leave the system. Okay, and then this system can also be extended to regions in space called open system, or in other words we call it control volume. So what happened in this is that now not just energy can enter and leave the system, but we also allow the mass to enter and leave the system. That is what we call open system. Alright, so this incoming and outgoing, of course you will create some kind of imbalance, right? So if the incoming is more than outgoing, so you will add additional into the system, either in the forms of mass or in the forms of energy, right? So these conservation relation are also called balance equation, since any conserved quantity must balance during a process. So whether you have a balance that is increasing or the balance that is decreasing in terms of mass and energy. Alright, so now let us look at conservation of mass. So the conservation of mass relation for a closed system, or in bracket control mass. So it's a closed system, so no mass can enter and no mass can leave, as I described to you before. So undergoing a change in is expressed as the mass in the system, m cis, equals to constant. So the mass in the system is constant, it doesn't change because we control the system, or we control the mass. Alright, so the changes of mass with time, dm cis over dt equals to 0. So there's no change of mass in the system, which is a statement that is the mass of the system remain constant during the process. So the mass in the system doesn't change, or doesn't change in the sense that it does not increase, it does not decrease, and it stays constant all the time. So it doesn't mean that it has to be 0. It can be 0. It also can be any number that is either equal or greater than 0. Okay, so the mass in the system can be either equal to 0 or greater than 0. So it can be any value. Alright, but that value will stay constant throughout the time. Alright, that's why we have dm dt equals to 0. The mass for an open system, or in other words we call it control volume, CV, in rate form, we have this conservation of mass, which is equals to m mass flow rate enter minus the mass flow rate going out equals to the change of mass in the control volume with time. Alright, the change of mass in the control volume with time. So in a simplistic form, you can draw this diagram. We have a system in the middle. We have an incoming mass and outgoing mass. Okay. So if the incoming rate of mass is greater than the outgoing rate of mass, therefore we have increasing mass in the control volume with time. So if the incoming mass is lesser than the outgoing mass, means the outgoing mass is a lot greater, then the mass in the system will be decreased with time. All right. So that's what you mean by this what I call mass balance equation. Okay, mass balance equation, or we also sometimes call it as a what you call that continuity equation. All right, continuity equation. So the M in and the M out here is given to you. The total rate of mass flow into and out of the control volume. All right, and the dm dt, okay, is the rate of change of mass within the control volume boundaries. All right. And this is what we call continuity equation. Okay, in fluid mechanics, the conservations of mass relation written for a differential control volume. Okay, so a differential control volume is usually called continuity equation. All right, now let us look at linear momentum equation. So linear momentum equation, the product of the mass and the velocity of a body is called the linear momentum, or just momentum of the body. So we take the mass, multiply with the velocity, we will get the momentum. Alright. So the momentum of a rigid body of mass m moving with a velocity v is mv. So take the mass of the rigid body, multiply by the velocity of the body, you will get the momentum of the rigid body. According to Newton's second law, the accelerations of a body is, okay, acceleration means this acceleration, okay, the a which is a back vector, the acceleration. The accelerations of a body is proportional to net force. So the F, okay, F is the net force, proportional to the net force acting on it, and is inversely proportional to its mass, okay, to its mass. So we take the F divided by the mass m. Okay, so a the acceleration will be directly proportional to the force but inversely proportional to the mass, and that the rate of change of the momentum. Rate of change of momentum here, you can basically look at the Vf minus Vi. So Vf is a V final minus V initial divided by t, which is the time, and therefore you get this what I call the rate of change of momentum. So that the rate of change of momentum of a body is equal to the net force acting on the body. So the Vf minus V1 Vi divided by t time, it will be proportional to the F, okay, proportional to the force divided by the mass. Alright. So conservations of momentum principle. The momentum of a system remain constant only when the net force acting on it is 0. Thus the momentum of such a system is conserved. So if the force acting on the system is 0, so the object can either in a stagnant form. If the object is in a stagnant form, it will stay stagnant forever. If the object is in a motion, the object will move with a constant velocity. Okay, will be moving with a constant velocity, with the condition that the net force acting on it is actually 0. Alright, so that's the conservations of principle, conservation of momentum principle. So linear momentum equation in fluid mechanics, Newton's second law is usually referred to as linear momentum equation. So F equals to m in the bracket Vf minus V1 close bracket divided by t, which is the time. Alright, so now let us look into conservations of energy. The conservations of energy principle, the energy balance. Right, the net energy transfer to or from a system during a process be equal to the change in the energy content of the system. So the energy that transfer into the system or the energy that transfer out from the system should be equals to the change of energy within the system. So you have a this called closed system. Alright, closed system. So the difference between the incoming and outgoing, you will have either increment or decrement of the energy in the system. Alright, so energy can be transferred to or from a closed system by heat or work. Okay, so remember the closed system. The closed system basically means no mass can actually enter or leave the system, but the heat or energy can actually enter or leave the system. So forget to mention also that is also work as well. Work can actually enter or leave the system, but the work is being done to the system, okay, or the work being done by the system. Okay, being done to the system or done by the system is different. Alright, so control volume also involve energy transfer via mass flow. Alright, so control volume, so you only control volume, you have mass inflow as well as heat or work, okay, in and out from the system. Alright, so now let us look at the conservations of energy. Conservation of energy basically means the rate of energy entering minus the rate of energy leaving, and therefore you have a rate of energy change within the control volume. Alright, so if the energy entering is more than the energy leaving the system, therefore you have a appreciation increasing or increasing energy of the system with time. If you have an incoming energy lower than the outgoing energy, what it means is that the outgoing energy is greater than the incoming energy, therefore you have a depreciation or decreasing energy of the system with time. Alright, so here you already being labeled E in is energy, okay, the rate of energy transfer into, and E out is a total rate of energy transfer out of the control volume, right? So and the CV is control volume and then E is energy. So the change of energy in the control volume with time is actually the rate of change of energy within the control volume boundary. Okay, so whether this is increasing or decreasing depending on the ingoing minus the outgoing energy. So in fluid mechanics, we usually limit our consideration to mechanical forms of energy only. Alright, so we will look at that. We'll look into what is the mechanical forms of energy. So now let us look at the conservations of mass. Conservation of mass, okay, mass like energy also is a conserved property, and it cannot be created or destroyed during the process. So the mass will stay the same as a mass. It cannot be created, it cannot be destroyed. Okay, so closed system, in the closed system, the mass of the system remain constant. So the mass within the system will stay the same, okay, during a process in a closed system. So a closed system, you does not allow the mass to enter or leave the system. It will stay in the system all the time, does not change in the amount. But in the control volume, the mass can cross the boundary. Not just that, but also the energy can cross the boundary. Same thing goes for closed system. Energy can also cross the closed system boundary. But in the control volume, not only energy can cross, but also mass can cross the boundary. So we must keep track of the amount of mass entering and leaving the control volume. Take for example, if you have 2 kg of hydrogen gas plus with 16 kg of oxygen, therefore you might have a chemical reaction that leads to the formations of H2O. Therefore you have a total amount of mass which is 18 kg. Though you have some kind of chemical reactions, but the total mass will still remain the same. Alright, so mass is conserved even during chemical reactions. So the mass and energy, mass is m, energy is E, can be converted to each other's given by the relationship of E equals to mc squared, and the c is the speed of light in a vacuum, and c is equals to 2.9979 multiplied by 10 to the power 8 meter per second. So and you must keep note that the mass change due to energy change is negligible. Okay, so now let us look into the mass and volume flow rate. Okay, so first we look into the mass flow rate. So the mass flow rate, the amount of mass flowing through a cross section per unit time. So to understand mass flow rate, it's easier to look into volume flow rate. Okay, so the volume flow rate is actually given by Q equals to AV. Okay, so the Q is the flow rate, volume flow rate. We have the unit of meter cube per second, and the Q is equals to A multiplied with V. So the A is the area of the cross section, and V is the velocity. So the velocity has a unit of meter per second, and the area has a unit of meter square. So imagine you have a cylinder, okay, and then you have a cross section which is A, and then the water is flowing through the cross section with the velocity V. So you have A which is m square, V which is meter per second. So if you take m square multiply with meter per second, you get meter cube per second, therefore you get the volume for it. Alright, so that's how it goes. So the velocity is always normal, is flowing normal to the area. Alright, so when we want to calculate the mass flow rate, you just take the density of water. For example, here is a liquid, let's say it's a water, so you must have the density. So the density of water will be rho. So the rho multiply with the volumetric flow rate, therefore it will give you the mass flow rate. So since the Q, the volume flow rate is meter cube per second, and the density of the water or the liquid itself is a kilogram per meter cube, and therefore you get kilogram. After you take rho multiply by Q, you get kilogram per second. So therefore the mass flow rate is actually kilogram per second. Alright, so if you expand this Q, you get the mass flow rate m with m dot equals to rho a v. Okay, so if you differential the mass, then you also get the differential of area. Okay, so in this case you can have this relationship. Okay, the purpose of this the relationship is to have a differential mass flow rate. Okay, is to have a differential mass flow rate. So a small amount of mass passing through this cross section, for example, will be depending on the density of the liquid, the velocity that is normal to the surface area, and the differential of the area. Okay, of the area. So if you are interested with the area between area 1 to area 2, so you can actually integrate the differential of area AC, and then we will get AC2 minus AC1, and the A, if you were referring to a flow in the pipe, then you get A is equals to pi r square. So it's pi r2 square, and this one is pi r1 square. Alright, so you have a difference of the area, which give you the area between area 1 and area 2. Right, and the same thing we can do the differential for the mass, and the path function have an inexact differential. Okay, so you do a differential, you get a total mass. So it's stated here that m2 not equals to m1. This is another thing that we will not talk in detail about, but what you can expect is that you can get a total mass that passing through the area between area 1 and area 2. Right, so here's a diagram also show to you that the velocity, the normal velocity for a surface is the component of the velocity perpendicular to the surface. So it must be perpendicular, it must be 90 degrees. The velocity must be normal 90 degrees from the surface area. Okay, that's how it's being done. So now let us look into this slide. Just now we talked about this mass flow rate. I show you from volumetric flow rate to the mass flow rate. Now from mass flow rate we can also look into volumetric flow rate. Okay, so just now we have these changes of mass flow rate equals to this rho v dA, right? So we can take this relationship and expand further by taking a derivative, and we know that we're taking a derivative on integration on both sides. We will get this mass flow rate. Okay, mass flow rate equals to the integration of mass flow rate, integration of the changes of the mass flow rate, also equals to the integration on the this rho v, which is the velocity normal to the area dA. Okay, dA, and then we could take out the, if you can assume that the density is actually constant, and you can move out the density, and if you take the integration on the velocity multiply with the dA, you get something like this. Alright, and then if you divide it with the area AC, cross-sectional area AC, and then you will get a V average. Alright, V average. So the V average is basically the velocity average. Okay, velocity average of the fluid flowing in the pipe. Alright, So if you allow the fluid to flow through to the pipe and allow that kind of flow profile to develop, so you will have a fluid that flowing very fast in the middle and a fluid that flowing gradually slowing as it get closer to the surface of the pipe. This happens because there is an attraction between the fluid flow and also the and also the internal of the pipe. So the attraction between the fluid and the pipe surface causes the molecule of the fluid to stick, or the atom of the fluid to stick to the wall. So the molecule or atom that stick to the wall, the molecule or atom of the fluid that stick to the wall does not move. That's why you get almost zero flow at near the wall and near maximum in the middle of the pipe. That's happening in the pipe flowing system. It's the same for liquid and maybe to a lesser extent to the gas flow. Alright, so generally speaking, you could assume this kind of profile develop. So that's why this is called the original velocity distribution in the piping system. And then if you try to take the average of all the velocity in the piping system, you will get a V average. So the average velocity. So the average velocity is the average of all these individual velocity profile in the pipe, right? So the average velocity VAVG is defined as the average speed through a cross section. Alright, so when you take the average, you got VAG. So VAG equals to 1 over AC, integrate the velocity that's normal to the cross section, DAC. Alright, so if you take the AC multiply with the VAG, okay, take the cross sectional area multiply with the multiply with the velocity in the pipe, therefore you get this volumetric flow rate. Okay, so we have a volume V with a dot here at the top, which is means divided by second, so it's a meter cube over second, so it is called volumetric flow rate. So you can look at this, V is the volume equals to meter cube, and you have a dot here, so you have a meter cube divided by the time. Alright, so if you integrate this area, alright, you will get this VA multiplied by AC. So you integrate this velocity normal multiply with the VAC, you will get V average multiplied with AC. Normally we will drop the AVG symbol. We will only write VAC. Okay, so this is basically the unit of meter cube per second, or the volumetric flow rate. Alright, so you can write this relationship to replace this term. Alright, here, therefore you get rho VAVG multiplied with AC, and you know that this VAVG AC is actually the V naught, or sometimes I would like to call it as Q. Also referring to the same thing, it's a meter cube per second. Okay, it's basically the same thing. The one that I showed you in the previous slide is referring to this Q. Alright, AV. Okay, then this also can be simplified further, because we know that this VAVG multiplied with AC is basically the flow rate, so we can actually replace it with a V dot at the top. So V dot at the top, then you'll get M dot, which is the mass flow rate, equals to the density multiplied with the volume flow rate, V dot, and then equals to V dot divided by the small v here, and this small v is actually referring to the specific volume. Alright, so it's basically the density equals to 1 over small v, or in another way of looking at this is that this is V volume divided by the mass. Alright, so if you invert it, you get the small v. This is specific volume. Alright, okay, yeah, so I hope you don't confuse with so many V here. So the V average is the V average is basically the meter per second, which is referring to the average velocity here. Alright, and then the average velocity multiplied with the area, you get volumetric flow rate. Okay, V dot dot here means divided by time, second. Alright, so we have a meter cube divided by second. So but the V without if the V only without the dot, you get the volume. Alright, the V without the dot, you get the volume, M cube. But if you have a V average, basically that referring to the velocity. and the A is always referring to the area, which is m squared. All right. So now let us look into explanation into the conservation of mass. Okay, in terms of its principle being used. So the conservation of mass principle for a control volume. So remember, control volume, we allow the mass to enter and leave the system. At the same time, heat and work also entering and leave the system, right? So the net mass transfer to or from a control volume during a time interval changes of t. So it means a small change of time, we have some amount of mass entering and leaving the system. So it's equals to the net change increase or decrease in the total mass within the control volume during a small change of time. So the total mass entering the control volume during a small change of time minus the total mass leaving the control volume during the change of time equals to the net change of mass within the control volume during the change of time. So if you look at the mass entering, okay, in the system, the mass leave the system equals to the change of mass within the system. All right. So let's say you put in you put in 50 kilogram. For example, here you put in 15 kilogram of water. All right, and then here at the bottom you take out 30 kilogram of water. So in the end, what happened to the mass within the system? The mass within the system gained 20 kilogram, right? And then if you divide it with time, okay, divide it with time, because you do it for a certain amount of time. Maybe this happened within 1 hour, 2 hours, depending. So you have a change of time, 1 hour or 2 hours, right? So if you take the change of time here, you divide it here, you get this the incoming flow rate, the incoming mass flow rate, the outgoing mass flow rate. Okay, so incoming mass flow rate minus the outgoing mass flow rate, you get the changes of mass within the control volume with time. Okay, so the m in dot m out dot is the total rate of mass flow into or out of the control volume, and the dmcv dt is the rate of change of mass within the control volume boundaries. Okay, so mass balance is applicable to any control volume. So for example, this bathtub is a control volume undergoing any kind of processes. So you have incoming and outgoing. All right, so not just limited to this incoming and outgoing, it could be multiple incoming, could be multiple outflow. All right, so keep in mind mass balance. Conservation of mass principles for an ordinary tub. So this statement is actually referring to this diagram, right? So the same principle can be applied to any kind of condition, because the most important thing is the incoming minus the outgoing equals to the changes within the control volume. Okay, now let's look into the perspective of this what I call water bath. Okay, the example ordinary bathtub. Okay, example. So we have a change of mass equals to the changes of volume, right? Changes of the volume multiplied with the density. So you can see the dm is the changes of the mass within the bathtub, for example, and then you have this what I call the density, which is kilogram per meter cube, and then you have changes of volume, right? So total mass within the control volume. So remember, control volume, you can allow the mass to enter and leave the system. At the same time, happen to the energy, okay, the work or the heat, okay. And then in the control volume, okay, therefore if you integrate this equation, you get the mass, okay, the mass in the control volume. You know how much mass in the control volume, and then you also have to integrate the control volume for the density multiplied with the changes of volume, okay, dV. All right, and then if you further divide it with time, and then you get this rate of change of mass within the control volume. All right, so you get this dmcv control volume divided with time, same thing, d differential of the integration control volume rho multiply with this dv divided by dt. All right, this is the kind of relationship you get if you develop with time from this relationship. Okay, the whole purpose is to know how much mass, okay, mass changes within the control volume. All right, so let us look further. normal component of velocity. So you have a velocity. Just now in the previous slide, we talked to you about this normal velocity. So the velocity has to be normal to the area, right? So sometimes the velocity is not normal. So what can you do is that you take the velocity, you multiply with the angle that is normal to the that is normal to the area. You might have a theta, right? So you take v, multiply with the cos theta, hence you get this v is also equals to v vector velocity dot n is a unit vector. Okay, unit vector. So if you study about vector and you know what is the meaning of unit vector, if you don't know what is the unit vector, it's okay, you can go and find out. Otherwise, you should know, you can assume that the velocity vector dot n unit vector multiply with a unit vector, you will get a normal velocity. Okay, normal velocity. All right. So if you look into the differential mass flow rate, okay, differential mass flow rate. All right, here you should have a differential mass flow rate. All right, so you put it here. You have a rho multiply with a normal velocity. Okay, multiply with a normal velocity. Multiply with with the small changes of area. All right, so the v normal is equals to v cos theta. Okay, v cos theta, which is also equals to v dot n. All right, v dot n. So basically, it just means that the density of the fluid multiply with the velocity that's normal to the area dA. All right, that's what it means. So if you integrate this equation, all right, then you will get the net mass flow rate. So the net mass flow rate is m dot net, okay, equals to integration through the control surface. Okay, so delta m dot, okay, equals to the integration of the control volume for the rho vn dA. All right, so the vn itself is a v dot n. All right, okay, so you can look into this diagram. This diagram will show to you, showing to you the control volume CV, and then you have a small area dA, and then you have a velocity that is not normal to the area, and then you know what's the angle, which is the angle to the directions that is normal to the area, which is given by theta. So you take v multiply with cos theta, then you get the Vn. All right, that's what it means. So there are reasons behind this kind of derivation. All right, but ultimately it's just you want to show to you that you have something that cross the control volume. Okay, you have something that cross the control volume, something that enter the control volume, something that leaving the control volume. So within the boundary you have a control volume. Something that enter the control volume, it must be through the control surface. Okay, so something that leaving the control volume also must going through the control surface. That's why you have a CS here. Okay, just they are trying to be more refined in what they're saying. So you have a control volume, something that entering the control surface, something that leaving the control surface. That's basically what they're trying to say. So the differential control volume dV and the differential control surface dA used in the derivation of the conservations of mass relation. All right, so that's basically what they are trying to point to you. So the mathematical expression, just the way how the mathematical equations are being applied, but the ultimate idea is just to get to you is that you have a control volume. You have a control volume equals to what's entering the control surface, what is going out from the control surface. So ultimately you will get the control volume. All right. Okay, now we come to the next slide, which shows to you the general conservations of mass. So before we look into this, I'll show to you the previous slide. So you can see that in the previous slide, I showed you the control volume. Okay, so the derivation for the control volume here I label as 1, and then I also showed you the next the net mass flow rate that entering or leaving the mass. Okay, yeah, I label it as number 2. So what's happening up on the surface, and either the mass is entering or leaving the surface. will ultimately equals to the changes within the control volume. So we already show you the control volume equation, okay, which is changing of the mass in the control volume with time. Then you have this kind of relationship. I also showed to you that how the mass can actually enter and leaving the control surface. Okay, so this is the boundary. We have control volume. We have substance that entering the boundary, also leaving the boundary. Okay, so if it enter the boundary, it will enter into the control volume. If it's leaving the boundary, it will leave from the control volume. So from control volume, we will leave through the control volume. Through the control volume, through the control surface to the outside. Okay, so if it's leaving, it will be losing. If it's entering, it will be gaining. So that's why you have a changes of the mass within the control volume with time. So we have these two equations. Equation 1, okay, the rate of change of mass within the control volume, and then equation 2, the net mass flow rate entering and leaving the control volume. Alright, therefore you have this relationship. Alright, the change in storage, which is given by this term, and then plus the entering or leaving the surface. You have a control volume and then a control surface. Right, and then we equal these two, you get equals to 0. Right, this is the general conservation of mass. Alright, so this equation can be rearranged. You can move it from the second term from here, from the left to the right. Okay, and then you just put a minus sign on the front. That you get a different forms of equation, but it's exactly referring to the same thing. So the time rate of change of mass within the control volume plus the net mass flow rate through the control surface is equals to 0. So what it's trying to tell you is that you have a control volume, okay, so the mass is changing within the control volume, and then you have a mass that entering or leaving the control volume. So then you plus them together, you should be getting 0. You can also rearrange this equation into this form and then ultimately into this form. Right, they are basically the same equation, it's just that being written differently. Okay, now we are looking in mass balance for steady flow process. Okay, what steady flow means? Steady flow basically means no change of mass in the control volume with time. Alright, so during a steady flow process, the total amount of mass contained within a control volume does not change with time. So the MCV equals to constant. Alright, so this basically means dmCV divided by dt equals to 0. Then the conservation of mass principle requires that the total amount of mass entering the control volume equals the total amount of mass leaving it. So if dmCV divided by dt equals 0, basically means m rate in, m rate out is equal. So no change. Okay, so in the control volume, the mass is always the same. Alright, so for steady flow process, we are interested in the amount of mass flowing per unit time. That is the mass flow rate. Okay, so the mass flow rate in, the mass flow rate out. So they are in kilogram per second. So you might have a multiple inlet. You also can have a multiple outlet, multiple exit point. Alright, so in a simplistic form, you can have a m1 dot mass flow rate 1 equals to mass flow rate 2. So it could be referring to inlet, and this one could be referring to the outlet. Okay, so the m1 flow rate, okay, is a rho 1 v1. V is the velocity, rho is the density, and A is the cross-sectional area. So similarly for the exit point, rho 2, v2, and a2. So this is basically a single stream. So single inflow and single outflow. You can have multiple inflow and also multiple outflow. Okay, it's the same thing. So many engineering devices such as nozzles, diffusers, turbine, compressor, and pump involve a single stream, only one inlet and one outlet. But here is an example showing to you the conservation of mass principle for two inlet. Okay, you have two inlet and then one outlet steady flow system. So you have two inlet M1, M2, two inlet, and then you have a one outlet M3. So right, you have 2 kilogram per second, and then another 3 kilogram per second as an inlet, and then it will ask you to estimate what is the M3 at the outlet. So the M3 at the outlet should be equals to M1, the rate of the mass flow rate for the M1 and the mass flow rate for the M2. So M1 plus M2. Okay, you get 5 kilogram per second. Alright, it can be a multiple outlet as well. Alright, okay, so this is a classical example of what I call mass balance for any control volume. You could get this kind of question in the exam. Mass flow rate is one of them. Volume flow rate is also another kind of calculations example that you are being asked in the exam. So please take note about it. Alright, so now let us look into a special case. We call it incompressible flow. Incompressible flow, the word compressible means something that can be compressed. But E for incompressible flow means that the substance cannot be compressed. So in this case, it's referring to the fluid. Okay, so the fluid cannot be compressed. So for example, for water is more nearly incompressible. So in this case, for water, you can assume that it is incompressible liquid. Okay, so incompressible flow, basically it happens in a condition where the density will be constant, because the density is given by the mass over volume. So if the volume does not change and the mass is also constant, therefore you have a constant density, right? So so in this case, if you look at this, if you have a mass flow rate, okay, the mass flow rate m dot equals to rho AV. So when the rho is constant, you can use it to model a system by just using Q equals to AV without having to consider the density, because the density is constant. So that's what it means, right? So if the density here is the same as the density here, therefore the rho can be ignored. So you just use the flow rate itself. You don't have to use the mass flow rate. But when the density is not constant, means that if the fluid is compressible, therefore rho will change. So it's more accurate that if you use the mass flow rate, so m equals to rho AV, to model the inlet to compare with the outlet, right? So now this is a special case. It's called incompressible flow. So in incompressible flow, you have a rho constant. So basically you can turn the mass flow rate into volumetric flow rate. So the conservation mass relation can be simplified even further when the fluid is incompressible, which is usually the case for liquid. So therefore you have a volumetric incoming flow rate equals to the volumetric outgoing flow rate. So volumetric flow rate is meter cube per second. So for many inlet and outlet, so you can use this equation. Alright, so you can have 2 inlet, 3 inlet, you have 1 inlet, 2 inlet, 2 outlet, 3 outlet, 4 outlet, you can have multiple outlet. Okay, so in this simplistic form, you can actually equals the inlet to the outlet, right? So you just use the volumetric flow rate, which is equals to V1 velocity multiplied with the area A1, okay, equals to the outlet V2 and the area A2, right? So this is true for condition where there is a steady state and incompressible flow, and this is true for steady state incompressible flow as well as single stream, because we only have 1 inlet and 1 outlet. Alright, so there is no such thing as a conservation of volume principle. So there's no such thing as conservation of volume, or volume conservation they do not exist. Okay, it does not exist for volume conservation. There is only mass conservation. Okay, so initially I talked to you about this conservation of mass, conservation of energy, conservation of momentum. So that kind of conservation exists, but conservation of volume does not exist, because conservation of volume is true only when the fluid is incompressible. So most of the time, if you deal with liquid, yes, this is true, but when you deal with gas, then this is no longer true. So this principle would fail. As a result, you should always refer to the mass conservation, because mass conservation is always correct, whether the fluid is compressible or incompressible. Alright. However, for a steady flow of liquid, the volume flow rate as well as the mass flow rate remain constant, since liquid are essentially incompressible substance. So this equation, the volumetric flow rate equation, is correct as long as the density does not change, especially for liquid form. During a steady flow process, volume flow rate are not necessarily conserved, although mass flow rates are. So that's why it is more safe to use mass flow rate equation than using volumetric flow rate equation, right? So because you don't know when the density would change, right? So if the density change and you did not take that into account, therefore your estimation will not be correct. But if you use mass flow rate, you have the velocity, you have the area, and then you know the density, then you always get a good estimation of the mass that's within the system. Okay, so let us look into this example 5.1. Water flow through a garden hose nozzle. Okay, a garden hose attached to a nozzle is used to fill a 40-liter bucket. So this is the bucket. Okay, this is the bucket here. Alright, the bucket here. So this bucket has to be filled up. This is 40 liter. Alright, 40-liter bucket. Alright, the inner diameter of the hose. So this hose. Okay, this is the hose. Okay, this is the hose. It has a diameter. It has a diameter of 2 centimeter. Alright, and it the hose, okay, and it reduces to 40 centimeter. Sorry, it reduces to 0.8 centimeter at the nozzle exit. Okay, nozzle. Okay, the tip here. Okay, is 0.8 centimeter diameter. Alright. So if it takes 50 seconds, okay, 50 seconds to fill up the bucket with water. So this bucket, it takes time 50 seconds, okay, to fill up the bucket. Alright, so now oops, okay, 50 seconds. Okay, to fill up the bucket with water. Now A, determine the volume. Okay, the volume and mass flow rate of water through the hose. Okay, through the hose. And B, the average velocity of water at the nozzle exit. So you must know that you have a bucket. The volume of the bucket is 40 liter. Okay, let me just use black color. So the volume of the bucket is 40 liter. You can also convert that into meter cube, which is 0.04 meter cube. Okay, meter cube, because 1 meter cube equals to 1000. Okay, 1000 liter. Alright, so you can take 40 liter divided by 1000, then you get 0.04 meter cube. Alright, and then you are given the hose. Okay, the hose diameter. The hose diameter of the hose is 2 centimeter. You can convert that into meter, 0.02. Okay, 0.02 meter. Alright, and the diameter at the nozzle. Okay, nozzle at the exit of the nozzle, you get 0.8 centimeter, which is 0.008 meter. Alright, and the time to fill up the bucket is T 50 seconds. Right, now A, determine the volume and mass flow rate of water through the hose. Okay, determine the volume and mass flow rate. Okay, the volume and mass flow rate through the hose. Okay, so the volume, the mass flow rate. Okay, to fill up the bucket
should be equals to the mass flow rate passing through the nozzle should be equals to the mass flow rate passing through the hose. Okay. So you have a hose, and then you have a nozzle. Okay, so this is a hose, this is a nozzle, and then you have a bucket to be filled up with water. Bucket. Alright, so the water coming in to fill out the bucket. Alright, so you can see the hose is 2 mm diameter. The nozzle is 0.8 the diameter of the hose is 2 cm. The diameter of the nozzle is 0.8. Okay, and then you are given the information about the bucket, the volume of the bucket, the time to fill up the bucket. So the time to fill up the bucket, the mass flow rate, should be equals to the mass flow rate flowing through the nozzle, should be equals to the mass flow rate flowing to the hose. So A, right, to calculate the mass flow rate, the volume flow rate, and the mass flow rate, so what can you do? So to calculate the volume flow rate, alright, so you must take the volume, you know, which is 0.04 meter cube. Okay, so you have the flow rate, sorry. Okay, maybe this one is better this way. The volume divided by the time. Alright, the volume of the bucket. The volume of the bucket is 0.04 meter cube per time. Time is 50 seconds. So in this case, you should get, let me just use the calculator, 0.04 divided by 50 seconds. So you get 8 multiply 10 to the power -4 meter cube per second. Right, so this is the volumetric flow rate, and then you are asked to find the mass flow rate. So the mass flow rate is equals to rho AV, or equals to rho V dot. Okay, so in this case is given by rho is 1000. The density of water is always 1000. Okay, multiplied by the V, which is 8.4 meter cube per second. So if you calculate that, you should get about 0.8 kilogram per second. So this is the mass flow rate. Alright, so you have a mass flow rate and the volumetric flow rate. So the A is done. B, you are asked to find the velocity, the average velocity of water at the nozzle. Okay, at the nozzle you must know the diameter of the nozzle, because the diameter is different at the nozzle and also at the hose. So you can use this equation, V equals to AV. Alright, AV. So your V is equal, okay, velocity correct. V is equals to V dot over A, which V dot equals to pi over 4 D nozzle square. Okay, so you get here is 8 multiplied with 10 to the power -4 meter cube per second, and here is pi over 4 multiplied with the diameter of the nozzle, which is 0.008. okay, 0.08 meter square. Okay, then what is the value? Now let us find the value. 8 multiply 10 to the power -4, right, divided by pi, multiplied with 4 divided by 0.008 square. We should get 15. Okay, maybe I should write it at below here. So it's 15.915 meter over second. Okay, so that should be the answer. So that's how you calculate the velocity at the nozzle exit. Okay, if you want to find the velocity at the hose, it's also possible. You can also do that, but you have to use the diameter of the hose, right? But the volumetric flow rate is the same, the mass flow rate is the same. All right. Okay, now let us look into the 5.3 mechanical energy and efficiency. Mechanical energy, the forms of energy that can be converted to mechanical work completely and directly by an ideal mechanical device, such as an ideal turbine. Alright, so the mechanical energy of a flowing fluid per unit mass. So mechanical energy, you have the unit which is joule, and then per unit mass we have the unit which is kilogram. So if you take joule divided by kilogram, you get joule per kilogram. So this is the equation for the mechanical energy of a flowing fluid per unit mass. So you can see here you got the flow energy, you got kinetic energy, and you also have potential energy. Okay, so the flow energy is given by the pressure, the kinetic energy is given by the velocity, and the potential energy is given by the elevation of the fluid, right? So if you just try to check the unit, the P divided by the rho, P basically the pressure, rho basically the density, V is the velocity, G is the gravity, and Z is the elevation. So the P, the pressure, you will have a unit of Newton per meter square, and then the density, you have a kilogram per meter cube. So if you try to simplify this unit, okay, you try to take a ratio of it, you get Newton per meter over kilogram. So Newton meter is basically given by joule, so you take joule divided by kilogram, that's what you get. Alright, and then the mechanical energy change. So if you have 2 points, point 1 and point 2, let's say you have a ground level, you have a point 1 and point 2. So point 1 is at the lower ground and point 2 at the higher elevation. So you take a difference of energy at these 2 points, you will get a difference of pressure at point 2 to point 1, and velocity point 2 to point 2, point 2 to point 1, and the elevation from point to Z1 to Z2. So this is basically how you try to compare the energy. And in a normal condition, you should if you obtain the difference between these two energy level, and if you found there is a difference, so possibly there is a input, okay, and if you found there is a negative, possibly there is a output, okay, out of it. So how do we know that? Okay, let's look into this. The mechanical energy of fluid does not change, okay. During flow, if it's pressure, density, so the pressure, the density, okay, the velocity, and the elevation remain constant. So the mechanical energy of a fluid does not change during flow if the pressure, density, velocity, and elevation remain constant. So if everything remain constant, so you will not have a change of this. So if you try to find a change between 2 points, if everything is the same, Z1 equals to Z2, Z2 equals to Z1, therefore you will have V2 equals to V1, P2 equals to P1, then you get a change of mechanical energy as 0, right? So that's what it means. So in the absence of any irreversible loss basically means friction loss. Friction loss created heat or work, okay, something like that. So in the absence of irreversible loss means there's no heat loss, there's no friction. All right, the mechanical energy change represent the mechanical work supplied to the fluid. Okay, so it means that the mechanical work supplied to the fluid if the change of mechanical energy greater than 0. Okay, so how could this happen? This happen in the stage when we use pump. We pump the water from lower elevation to higher elevation, so we provide energy to the system. Alright, so you have a change of positive energy, or extracted from the fluid if the change of mechanical energy less than 0. How does that happen? Maybe you allow the water to flow from high elevation to low elevation. So as the water flow from high elevation to low elevation, you install a turbine at the bottom. So you use the turbine to extract the energy from the fluid,
That's how we generate this hydroelectric energy, and this is an example of extracted from the fluid. So if the mechanical energy change is less than 0, so it means that energy is being extracted, being taken from the fluid. Alright. So mechanical energy is a useful concept for flows that do not involve significant heat transfer. Means there's no heat loss, no friction loss, okay, or energy conversion, such as the flow of gasoline from underground tank into car. So basically, it's a simple transfer of flow energy, kinetic energy, and elevation energy, okay, or potential energy. So now let us look into this mechanical energy conversion. Alright. So the usefulness of the mechanical energy equation is that we can use it to compare from one place to another, from one location to another. Right, so in this case, it's quite kind of useful here. We want to know how much energy actually being taken up by a turbine. So we have a water at the upstream, and then the water from the upstream will flow through the downstream. So here we can compare 0.1 with 0.4. Actually, the complete diagram is that you have a 0.1 here at the top, 0.4 at the bottom, and then 0.2 at the point before you enter the turbine, and the 0.3 at the time when you leave the turbine. So you have 4 points here. So we can compare different points. At each comparison, we can only compare 2 points. Alright, so we can use the equation multiple times to compare different locations. And you must be in this case, you must be good in picking up place of comparison. So there's no saying that which part of comparison is correct. So you must have a good judgment where at what points you should pick for comparison. So in this case, this is an example show to you that they have picked comparison between 0.1 and 0.4, and then 0.2 with 0.3. So here I label as A for the left figure, and for the right figure I label it as B when they compare it for just turbine, before and after the water flowing through the turbine. And okay, so if you look into this, if you look into the previous equation, okay, so you have this kind of mechanical energy of a flowing fluid per unit kg. So what I want to do is that I want to divide this equation with gravity. So if I divide this equation with gravity, is that I take the P pressure over rho g plus V square over rho over 2g plus Z, because I divide the whole thing with gravity. So end up I get the equation something like this: P over rho g plus V square over 2g plus Z. Okay, because I already divide that equation with gravity, so I can compare for two sides. So if you notice that this term, each of this term has a unit of m. Okay, so it's basically the head. Okay, the pressure head, the velocity head, and the elevation or potential elevation head. Okay, so we compare 0.1 and 0.4. So we write a complete equation for P1 divided by rho g plus V1 square divided by 2g plus Z1, because the only thing that difference for them is the pressure, velocity, and elevation. So density, we always assume that to be constant in the case of water, okay, in the case of liquid. But when it comes to gas, this is different thing, right? So gas, we don't use this kind of equation that much. Only equation, only for liquid, we use this kind of mechanical energy equation. Okay, so we compare 0.1 and 0.4. So we put P1 over rho g plus V1 square over 2g plus Z1 equals to P4 at 0.4 over rho g plus V4 square over 2g plus Z4. Okay, and then we have another plus here is H. Basically H is referring to the meter height. Okay, H turbine, we call it H turbine. Alright, so if you look exactly how is that H turbine appear on the right hand side, it's very simple. You see the water flow from 0.1 to 0.4. When the water flow from 0.1 to 0.4, the energy changes from elevation, okay, to pressure, to kinetic, and then it enter the turbine and then leave, and then to the ocean, okay, to the river, to the downstream. All right. So what you can see here is that the energy from here, from 0.1 to 0.4, is being lost, and the energy before it reached 0.4, some portions of the energy is being taken up by the turbine. All right. So it's obvious that some energy from here is converted into turbine, and some remain in the level 4 energy. Okay, then some will be taken up by the 0.4. Right, so we have a 0.1 energy, some portion contribute to the turbine, and some portion contribute to the 0.4. Right, so you have a 0.4 plus turbine energy will be equals to the 0.1 energy. That's what it means. Okay, so if you look at this equation, we can basically say that at 0.1 and 0.4 we have an equal pressure. All right, equal pressure. Why? Because 0.1 is at atmospheric pressure. 0.4 is also at atmospheric pressure. All right. Okay. So both side 0.1 and 0.4 have equal pressure. So we can actually cancel it out. In this case, we put it at 0. Okay, put it at 0 because we know that it's going to cancel out. Okay, and then the other thing is the velocity. The velocity. If you go up here in this area, if you look at the water will look more or less constant, doesn't change, doesn't move that much. And if you go to the 0.4, if you look at the water also look more or less stagnant, calm, not moving that much. So basically you can assume that the velocity at 0.1 and 0.4 is near 0. So you can also put at 0 and 0. Alright, so now leave us with the Z1. So we have an elevation at Z1, and then you have elevation at Z4. We must have a reference point. We can pick a reference point somewhere here, we can pick a reference point somewhere here, or we can pick a reference point at 0.4. So if we pick a reference point at 0.4, then Z4 will be 0, then Z1 will be Z1 minus Z4, then you should have H. So in this case, we just leave it as Z1, and then at Z4 we leave it as Z4, and then of course we also left with the H turbine. So we already know the pressure is 0 because it's atmospheric pressure. We know that the velocity is also 0 because the water is not moving that much at the surface. So 0, 0, 0. Then we have H turbine equals to Z1 minus Z4, which if you look at this, Z1 minus Z4 is basically given by H. So you have a H here. So H, if you multiply with mass flow rate and the gravity, therefore you will get watts. Okay, so watts basically is the Newton meter over second. Okay, or it's actually joule over second, so which will give you the unit watts. Okay, so watts is the power. All right, the power of what? Power that taken up by the turbine because of the energy, because of the water flowing from 0.1 to 0.4. Okay, so if you look at this equation, the watt, okay, the power, W dot max equals to mass flow rate multiplied by the gravity multiplied by the elevation difference Z1 minus Z4, which is M dot mass flow rate multiplied by gravity multiplied by elevation, okay, H, and then you get this Newton meter per second, or Newton meter, which is joule. Okay, then you multiply with per second, and then you get watt. Okay, so you know that P1 equals to P4 because at atmospheric pressure, V1 equals to V4 equals to 0 because they are almost not moving at the surface. All right. Okay, now if we try to compare 0.2 and 0.3, similarly we can write the same mechanical energy equation. All right, so P2 rho divided by rho g plus V2 square divided by 2g plus Z2 equals to P3 divided by rho g plus V3 square divided by 2g plus Z3 plus H turbine. So you can see that the water coming in has some form of pressure, velocity, elevation, and then leaving the point, leaving at exit point, it has some portions of pressure, kinetic energy, potential energy, as well as some energy taken up by the turbine. All right, so we can easily cancel out the velocity because we know that the pipe diameter is the same as inflow as well as the exit point. So the incoming point and the exit point, the diameter of the pipe is the same. So the velocity you expect to be the same, it can be cancelled out. And then we further assume that 0.2 and 0.3 has almost the same elevation. Okay, therefore Z2 can cancel out with the Z3. And then of course we were left with the pressure P2 minus P3 divided by rho g equals to H turbine. So you just multiply this whole thing with mass flow rate gravity, then you get something like this. All right. Okay, so you can cancel out the gravity, so you get a simplified form, and you could assume that the energy estimated with this comparing point 1 and point 4 equals to the energy at comparing point 2 with point 3. Okay, so in this case, if you can predict this, you can calculate W1, then you can use W1 equals to W2, which can help you to determine the pressure difference. But if you know one of the pressure, then you could predict the other pressure. All right, so that's how useful it is by using mechanical energy equation. All right, so later on we will show to you that this is also a Bernoulli equation. All right, and also show to you how this equation can be derived in a different ways. Okay. Okay, this diagram is to show to you that how we can actually compare the energy level. Okay, so the available mechanical energy of water at bottom of the container is equal to the available mechanical energy at any depth, including the free surface of the container. So you can see that what they want to say is that the mechanical energy at the surface is the same at point A, is the same as point C, is the same as point B. So we can do a simplistic comparison between point A and point B. For example, if you look at here, we can write this equation out, and then we could cancel out rho A, as we know that we can cancel out PA, the pressure at A. We know that it is at the atmospheric pressure, and if you take the gauge pressure, that it will be 0. All right, will be 0. If you want to maintain it, it also can, but you just get a P atmospheric here, and then PB will be atmospheric plus the elevation of water. Okay, in order to give you the PB. Alright, so if you assume that atmospheric as can be cancelled out, so this one will be 0, and this one is only the gauge pressure. So it means it's only based on the height of the water at the bottom of the tank. Then the velocity at the top, as usual, since it's a free surface, you can assume it as 0 because not much movement at the top of the water, and then at VB also not much velocity movement, can also be cancelled out, and then ZA is at the top and ZB is at the bottom. If you pick ZB as a reference point, then of course ZB will come 0. Then here we don't have turbine, that's why we don't have to write turbine put. I just wrote turbine here to show you that when there's no turbine, there's no need to have a turbine. If you put a turbine here, it also can be cancelled out. All right. So when you simplify this equation, you get PB equals to rho G ZA. So if you know the elevation of the height of water, then you can predict the pressure at point B. So pressure at point B equals to rho G ZA. Or in the previous chapter, in the statistic in a previous chapter, you know that point at the bottom of the tank is equals to rho G H. Right? So H is basically the height of the liquid on top. Okay, so what you want to show you is that the mechanical energy at given by pressure, velocity, and elevation, they are all the same at point A equals to point C equals to point B. All right. Okay, now let's look at the shaft work. Okay, shaft work is the transfer of mechanical energy is usually accomplished by a rotating shaft. Okay, so it means you look at something like a motor. Then you have a rod that is spinning, that is a rotating shaft. The rotating rod is called the rotating shaft. Okay, so the motor connect to the rotating shaft, and then to some kind of rotor, something like that. Okay, so shaft work is a transfer of energy either from the motor to the shaft or from the turbine to the shaft. Okay, so if it is a pump, there will be electrical energy from a motor to the shaft, and then from the shaft to the water, because you're using pump. All right. If you are using turbine, so the energy will be coming from the water to the shaft, and from the shaft to the generator, something like that. All right. So shaft work, the transfer of mechanical energy is usually accomplished by a rotating shaft, and thus mechanical work is often referred to as shaft work. Okay, a pump or a fan. All right, the job of the pump or fan is to give energy. Right, you convert the electrical energy into
some kind of kinetic energy, or you provide the energy from convert the energy from electrical energy to the energy that being absorbed by the water. So a pump or a fan receive shaft work usually from electrical motor. So the motor spin the shaft, so the shaft will get the energy and then transfer it to the fluid as mechanical energy in the less frictional losses. Alright, so during the transfer there could be some losses as well due to friction, okay, or you call it head loss, something like that. And then in the turbine, I convert the mechanical energy of a fluid to a shaft work. So in the turbine, if you see like hydroelectric dam, so we have a turbine at somewhere somewhere between the top and bottom of the water flow. So this turbine will be spin by the water flowing downward. So the spinning turbine will convert this kind of kinetic energy into the shaft work, and the shaft work will give the energy to the generator, and then the generator will give the energy to the what I call transformer, and then the grid to generate electricity, right? Okay, so the basic idea of this is that the reason we are talking about this is that because we are interested in the efficiency, okay, the mechanical efficiency, right? Mechanical efficiency of a device or a process. So the mechanical efficiency is equals to the mechanical energy output divided by the mechanical energy input. So you have a input of mechanical energy, and then at the top you have a mechanical energy output. So if you take 1 minus, this is also equals to 1 minus mechanical energy loss divided by the mechanical energy input, right? So the effectiveness of the conversion process between the mechanical work supply or extracted and the mechanical energy of the fluid is expressed by the pump efficiency and turbine efficiency. Pump efficiency, basically you have mechanical input, power input, which is coming from electricity, for example, or the shaft itself. And then you have a mechanical power increase of the fluid. So you transfer the energy to the fluid. So the fluid should obtain certain amount of energy, right? So that's why you have an increase in the mechanical energy in the fluid. And the energy is coming from the shaft, right? Because the energy in the shaft also coming from electricity. So you have two stages of conversion, from electricity to the shaft, from the shaft to the fluid. So the efficiency of the pump is from the shaft to the fluid, right? So from the pump to the fluid, okay? And then you also have this mechanical efficiency of a turbine. So the mechanical efficiency of the turbine is given by the mechanical power decreases in the fluid. So the mechanical power decreases in the fluid, transfer that energy to the shaft, right? So the energy will be taken up by the shaft. So that's why you have a mechanical energy power output, which is the energy taken up by the shaft divided by the mechanical power decrease in the fluid. So the fluid in the turbine, when the water flow from top to bottom, like a hydroelectric generator, so the power lost certain amount of energy. So the energy that it lost, it gives to the turbine. So the turbine get the energy and pass it through the shaft. That's why you have a loss of energy from the fluid going to the shaft. Okay, so this is how mechanical efficiency calculations are being done. Alright, so for a shaft or pump, there are different way of calculation. Alright, okay, after we understand the mechanical efficiency calculation, okay, now let us try to use this understanding so that we can actually calculate the mechanical efficiency based on an example. So here we have an example showing that there's an energy provided by a fan. Okay, so the fan is used to force an air to pass through a certain area. Okay, a certain area. So the fan provide 50 watt of energy through the shaft. All right, and then we want to know how much energy that is actually given to the fluid. Okay, so now we try to find out. So in the simplest way to find out is that we can use the what we call mechanical energy. Okay, we can use the mechanical energy equation. So we wrote back the equation for P1 over rho g plus V1 square over 2g. So we do that for point 1 compared with point 2. So one of the obvious things we can compare and compare point 1 and point 2 is that we can see that point 1 and point 2 actually at the same elevation, right? Okay, so obviously when we wrote this equation, we can see that the Z1 and Z2 will be cancelled out eventually. And one of the things we should also realize that just now, all this while we've been talking about turbine, now we have a fan that is giving energy into the fluid. So in this case, we have the what I call mechanical energy equation, and then plus the fan, the energy given by the what I call fan, okay, or you can also call it as a pump, but in this case it's fan. Pump will also do the same thing, it will giving energy. So the fan give the energy to the system. That's why we have a energy that in a point 1 plus the energy given by the fan. So we have an energy, existing energy at point 1 plus the energy given by the fan will be equals to the energy at point 2. So whatever kinetic energy that's given at point 2 should be coming from the fan, because point 1 and point 2, if no additional energy being provided to the system, they should have the same mechanical energy. Alright, so in this case, we'll try to compare, see what kind of terms we can cancel out. We can see that at point 1 and point 2, obviously they will have the same pressure, because point 1 we were exposed to the atmosphere, point 2 we also expose it to the atmosphere. So in this case, pressure at point 1 and pressure at point 2 should be the same. So P1 and P2 will be cancelled out. And then V1 and V2, obviously it's not going to be the same. At V1 you have a calm air, relatively calm air, compared to V2 the air will be moving at a lot faster than at point 1. In this case, we can cancel out point 1 V1 and then remain V2. And at elevation at the Z1 and Z2, they are the same. So in this case, we cancel out Z1 and cancel out Z2. So we can write an equation, H fan, height of fan equals to V2 square divided by 2g. Okay, divided by 2g. So we can multiply with mass flow rate and gravity. So you will get mass flow rate m dot multiply with V2 square divided by 2. So this will be the unit in watts, because mgh, m mass rate multiplied with gravity and h fan will be given in the unit of watts. Okay, so we know the mass flow rate here is given as 0.506 kilogram per second, and then the velocity at V2 is 12.1 meter per second. So we can calculate that the power is 37 watts. So we know that initially it's given 50 watt. Now the kinetic energy obtained by the air is only 37. So we take 37 divided by 50. We have a mechanical efficiency of 0.74. Okay, so if we multiply with 100, you get 74% efficiency. So the amount of energy provided by the fan, only 74% is given to the air. Okay, the rest around 26% was lost. Okay, due to friction, due to heat loss. Okay, so the mechanical efficiency of a fan is the ratio of kinetic energy of the air at fan exit to the mechanical power input. All right. Okay, now let's look into other forms of efficiency. Okay, so we can also look into motor efficiency. So motor efficiency, you can look at it as a that supply to the through the pump or through the fan. Just now we talked about fan. All right. So the motor is is referring to the mechanical. Means it convert the electrical energy through the motor to produce the shaft work. Okay, the shaft work. So the shaft spin, right? So it comes from the electricity. So you have electricity in,
and then you have a shaft work. So you have an electrical power input, and then at the top you have a mechanical power output. So electrical power input turn into shaft work. So you get electricity converted into a spinning of the shaft. Alright, so in order for the pump to move, for the fan to move, that's what it means. So this is called motor efficiency. And then the other one is the generator. Okay, generator, we have a generator efficiency. So the generator, you get the energy from, let's say you get the energy from the water, and then you convert the energy from the water into the shaft work. Okay, and then from the shaft work you convert the energy into electricity. All right, so the generator efficiency is referring to the shaft energy converted into the electrical energy, that is through the generator. Okay, that's through the generator. So you take the electrical power output divided by the shaft input, then you get the generator efficiency. All right, so and then you know that there is a series of process. For example, if you use pump, so first you must have electricity, and then the electricity must cause the shaft to move, and then the energy from the shaft will be given to the fluid through the pump, right? Or if it's a fan, it's also through the fan, right? So you go through two processes. You go through the motor that convert the electricity to the shaft work, and then you go through the pump which convert the shaft work to the water, convert the shaft work from the pump to the water. So it means it provide the energy to the water, right? So first of all, motor has its own efficiency. Motor is not 100% efficient, means some energy is lost as a result of conversion from the electricity to the shaft work. How is the energy lost? The energy lost in the forms of friction, in the forms of noise, in the forms of heat. Okay, and then another loss encounter when the energy is converted from the shaft work to the water. Okay, so you know, to do that, you can convert it through pump. You can also convert it to fan, right? So the shaft energy is converted into the energy into the water through pump or through fan. All right, so that we have another loss. All right, so we have two loss here. So the loss resulted from the motor, and the loss resulted from the efficiency of the pump or the fan, right? So if you multiply these two efficiency, then you get the overall efficiency. All right, you get the overall efficiency. So initially you get electricity, that's the original electricity, and then in the end only a portion is that being absorbed by the water, only a portions of the energy being absorbed in the forms of mechanical energy by the water, right? So if you combine motor and pump, then you have a pump motor overall efficiency. You just need to multiply that individual efficiency together. So if you look into the case of turbine generator overall efficiency, so here is an example of turbine generator. Okay, so the turbine generator is a reverse of pump motor or fan motor efficiency. So how does that happen? Because the turbine is that you take the energy from the water, so you extract the energy from the water. All right, so once you extract the energy, you convert the energy, the mechanical energy from the water into shaft work, and then because of that, some portion is lost. In this case, you see that only 75% efficiency, means of all the 100% that taken from the water, only 75 of it is given to the shaft work. And then from that 75%, another 97% efficiency actually take place, means another 3% is lost from the 75% energy that converted from the water. So from mechanical energy from water converted to the shaft work, from the shaft work it convert to the electrical energy, and as a result of this conversion, 97% is converted, 3% is lost. All right, so if you want to know the overall efficiency, you need to multiply the turbine efficiency with the generator efficiency. So 0.75 multiplied with 0.97, you get 0.73% overall. So in this case, the overall efficiency given by turbine and generator. So just multiply it. So you have you extract the energy from the mechanical fluid, and then you convert it to electrical output. All right. So that's how it works. Okay. So the overall efficiency of turbine generator is the product of efficiency of the turbine and the efficiency of the generator, and represent the fractions of the mechanical energy of the fluid converted to electrical energy. Alright, so this slide is talking about the efficiency. Okay, the efficiency defined range between 0 and 100%, right? So it can convert from 0% efficiency to 100% efficiency. So 0% efficiency corresponds to the conversions of the entire mechanical or electrical energy input to thermal energy, and the device in this case function like a resistant heater. Basically means nothing is being converted. You put 100%, if we provide 100 watts, 0 watt actually being converted. So all the energy being converted into thermal energy or being lost in the forms of resistance. Alright, so 0%, that's what it means. 100% correspond to the case where there is a perfect conversion with no friction and or other irreversibility, and thus no conversion of mechanical or electrical energy to thermal energy. So no loss. So 100% basically refer to the perfect conversion, means no loss in the forms of thermal energy, no loss in the forms of resistance. All the energy, let's say you provide 100 watt being converted to another forms of mechanical energy directly. No loss in any way. So it's a perfect system if you get 100% conversion. So of course, in reality, we get between 0 and 100%. Right? For systems that involve only mechanical forms of energy and is transferred as shaft work, the conversion of energy is given by the mechanical energy input minus the mechanical energy output, and you get a change of storage, a change of mechanical energy for the system, and also plus the losses. So these are the losses caused by the friction, resistance, or the heat loss. So these are irreversible, means that if you convert it back to the original source of energy, you will never get it back, the energy, because energy is lost in the forms of friction and heat. All right. So mechanical loss, okay, mechanical loss, the conversions of mechanical energy to thermal due to irreversibility such as frictions. All right. So many fluids flow problems involve mechanical forms of energy only, and such problems are conveniently solved by using mechanical energy balance. So if you look at this example, we have a pump that placed between two reservoirs. So you want to pump the water from one reservoir at the bottom to a higher elevation at reservoir 2. So we can actually basically compare energy at point 1 to energy at point 2. So in between, they are connected by a pump. So the purpose of this pump is to bring the water from a lower elevation to a higher elevation, right? So we can have can write a mechanical energy equation here for point 1 and point 2. So you can also notice that since we put a pump here, so the energy from point 1 to point 2 definitely we were added by a energy given by the pump. So we write here as a H pump. Okay, so mechanical energy at point 1 plus the energy coming from the pump equals to the energy at point 2, and we plus a loss here. The reason we put a loss here is because we might have some losses as a result of heat loss, result of resistance in the pump, resulted by the pump, or also due to the friction within the pipe. There are minor loss, major loss. This thing we are going to talk about that later on, but currently we just tell you that there are some losses in the pipe due to friction, losses in the pump due to friction, also heat generation, stuff like that. Alright, so when you look into this equation, if you try to solve this equation, you can see that point 1 and point 2, they are open to the reservoir. As a result, we have a pressure P1 and P2 can be cancelled out because both pressure at P1 and P2, they are at atmospheric pressure. So equal atmospheric pressure cancel out. Alright, V1 and V2, they are both reservoir. At the reservoir, if you look at the surface at point 1 and you look at the first surface at point 2, they are relatively constant, not moving that much. As a result, the velocity here and the velocity here, velocity at V1 and the velocity at V2, they are almost equivalent, almost near to zero, and they can be cancelled out as well. So end up you have you arrange this equation for H pump equals to Z2 minus Z1 plus H loss. So if you want to convert it into power, so you just multiply with mass flow rate and gravity, so you get this equation. So it's the same equation written here. So this is how these equations are being obtained. Alright, so let us look at this example 5.3. So example 5.3 is looking at performance of a hydraulic turbine generator. So you can see that there's a water flowing from point 1 to point 2, and as a water flowing down from point 1 to point 2, it is flowing through a turbine. So what happens is that as the water flow down, it spin the turbine, it spin the blade in the turbine, which leads to the spin of the shaft, and then leads to the generation of electricity by the generator. So basically there's a transfer of mechanical energy from water to the turbine, from turbine to the shaft, from shaft to the electricity passing through, generated by the generator. Alright, so let us look into the question. The water in a large lake is to be used to generate electricity by the installation of a hydraulic turbine generator. The elevation difference between the free surface upstream and downstream of the dam is 50 meter. So basically means if you take Z1, okay, let me just make some changes here in the size. If you take Z1 minus Z2, so you get about 50 meter. Okay, alright, and then the water is to be supplied at a rate of 5,000 kilogram per second. So the mass rate is 5,000 kilogram per second. Alright, and then if the electricity power generated is measured to be 1862 kilowatt, so means the electricity is 1862 kilowatt generated. Alright, and then the generator efficiency. So generator let me see, generator efficiency is 0.95. Alright, and then A, you are asked to determine what? The overall efficiency. Okay, the overall efficiency means turbine and generator. Okay, turbine and generator efficiency. Alright, need to find out this value. Alright, so let us begin by solving this equation by using this mechanical energy equation. So we can write point 1. Okay, point 1 energy. So you can see that the energy from point 1 flowing to point 2, the energy is being distributed between point 2 and turbine. So the energy from point 1, some of it is spent for the turbine and some of it will be arrived at point 2. So as a result, we will have something like this. Okay, so we have something like this, and keep in mind that how to say it? Keep in mind that the how to say, the pressure at point 1 and point 2, they are at atmospheric pressure, so basically we can cancel out because it will be the same. And then the velocity at point 1 and point 2, they are also near to 0. They are the same and near to 0. Because why? Because it is a free surface, and the water at the free surface is almost constant, all right, not moving that much, so we can also cancel out. And then now it leaves us with the H turbine, which is given by Z2 minus Z1, and we know that from sorry, it is Z1 minus Z2. Alright, so we know here that Z1 minus Z2 is 50. Alright, it's 50. Alright, it's 50 meter. Okay, and we can change it into we can change it into the power that transferred to the turbine. Alright, so just write as turbine. Okay, H turbine. Okay, we change it to turbine. We change it to the power turbine by just simply multiply the H turbine with the mass flow rate and gravity. So in this case, we have mass flow rate, which is 5,000 kilogram per second, and the gravity is 9.81, and then the H turbine is 50 meter. So if we try to do the calculation, we should get about 2452.5. Okay, 2452.5 kilowatt. Alright, so we get H turbine. Okay, to get this okay, to get this we call that the overall efficiency for turbine and generator. So we must know the mechanical energy that is being given, transferred to the turbine. Okay, and then we must also know the electricity that generated as a result. So what can we do here? So we must take the power of electricity generated, okay, over the W power given to the turbine. Alright, so in this case we have 1862 kilowatt divided by 2452.5 kilowatt. So the answer we have here is 0.7592. Okay, 0.7592 efficiency. Okay, now in the B we are asked to find the mechanical efficiency of the turbine. So we need to find the turbine. Okay, to find this, we can just simply take it's a turbine generator equals to the efficiency of turbine multiply with the efficiency of the generator. Right, so we already know the overall efficiency, which is 0.7592, and then the efficiency of the turbine, which is what we want to find,
and the efficiency of the generator is 0.95. Right, so the efficiency of the turbine would be 0.79918. okay, right? So then now we are looking into the question C. Question C, we are asked to find the shaft power supplied by the turbine. Okay, the shaft power supplied by the turbine. Shaft power. So we know the efficiency of the turbine. Alright, and we know that the mechanical energy transfer to the turbine, okay, should be equals to the this should be on top, that should be the power of the shaft. Okay, should be the shaft power. So if you want to find the shaft power, we take the efficiency of the turbine multiply with the power of the turbine, okay, which is efficiency of the turbine is 0.79918 multiplied by the power of turbine. The power of turbine is 2452.5 kilowatt, right, which would give us 191960 kilowatt. Alright, so that's how we solved the problem for example 5.3. Okay, so now let's look at the Bernoulli equation. So the equation, the energy equation that I've been writing for all this time is actually referring to this Bernoulli equation. So I've been showing you P equal P divided by rho g plus V squared divided by Rg plus Z. So all these terms combined, they are actually Bernoulli equation. But they, if you write it in a different form, you can also call it as a mechanical energy equation, right? So now you realize that the equation I've been using is actually a Bernoulli equation, but it's actually a modified Bernoulli equation because we include this frictional loss, stuff like that, right? So okay, anyway, let's just look at what is Bernoulli equation. So Bernoulli equation is an approximate relation between pressure. So we have a P, pressure, velocity, we have a V here, and we have elevation, which is the Z, and it's valid in the regions of steady, means steady flow, means if the P is 100 kilopascal, it's always 100 kilopascal, it doesn't change. V, when it's 5 meter per second, it's always 5 meter per second. That's called steady. Alright, steady. And incompressible flow, okay, so the flow that is incompressible basically means that the density is always constant, and where the net frictional loss, okay, frictional forces are negligible, so means that no head loss. So we will look into that in a different chapter. Frictional loss actually can be two kinds of loss: major loss, minor loss. Okay, so frictional loss means the thing that being transformed into heat. Okay, so the energy being lost. So in this case, when you write the Bernoulli equation, in the original forms of Bernoulli equation, it has no frictional loss, okay, or no frictional force. So despite its simplicity, it has proven to be very powerful tool in fluid mechanics. All right, so you see, we have used these forms of equation in our many previous examples, so you can see that these forms of equations are actually quite powerful. All right, so Bernoulli approximation is typically useful in regions outside of flow of boundary layers and wakes. So boundary layers, this is the boundary layer, okay, the boundary layer, and wakes is behind it, okay. So this layer is actually the viscous region. All right, viscous region. Outside of this region, we have a inviscid region. Okay, so I forget to mention, this is like an object, okay, an object placed in the fluid.
So you have a liquid, also you have a fluid coming over, okay, flow against this object, and the fluid will have to flow, pass through the boundary. Some pass through the boundary, some go above the boundary, some go below the boundary, some are far away from the boundary, some have to hit at the tip of the object and then stops moving. So you can see this line, blue line, is a path flow of the fluid. Okay, so when this happen, we create two region. Okay, we have a viscous region and an inviscous region. So outside of this region, we call it inviscous. Okay, inviscid region. Inside this region, we call it viscous region. So outside this region, we call it not viscous. Inside this region, we call it viscous. So the viscous region can be divided into two regions. We have a boundary layer. Okay, so it's like a layer of protection, but which is viscous. And then at the back, we have this wake. So it's like a spinning, rotational spin of the fluid particles. Okay, of the fluid particles, you can see that fluid molecule. So it is spin in the rotational form. So that's called wake. Okay, wake. So Bernoulli approximate is typically useful in flow regions outside of boundary layers and wake. So this is boundary layer, and this is at the back. This is wake. So outside of this region, the Bernoulli equation will be very useful. Okay, where the fluid motion is governed by combined effects of pressure, gravity. Okay, so you have a pressure, you have gravity, also the velocity. All right. So outside of this region, we have a region where the Bernoulli equation is correct. Okay, can be applied. All right. So the Bernoulli equation is an approximate equation that is valid only in inviscid region. So inviscid regions outside. Okay, outside here, in inviscid region of flow where net viscous forces are negligibly small. So as I mentioned to you, we have a viscous region here, and outside of it is not viscous. Okay, outside of it not viscous. So when the flow is in laminar, it is not viscous. When the flow is in turbulence, it is most of the time more viscous. Okay, all right. For this example, this is true. Right, compared to the inertia, so the net viscous force are negligibly small compared to the inertia. Okay, gravitational and or pressure forces. So such regions occur outside of boundary layers and wakes. Okay, all right. So this slide shows the derivations of Bernoulli equation. So if you follow the steps of the derivation, you can see that it used the force. Okay, the Newton force, to actually come to the derivations of the Bernoulli equation. So in the end, you can see that you have this flow, you have a kinetic, and also the potential energy. So this is true only when we use it for steady flow, and we use it for incompressible flow. Alright. So the Bernoulli equation between any 2 points on the same streamline is shown here, and this example, this kind of comparison method I have shown to you in many previous slides. We can use that to find the H turbine, the H pump, H fan, okay, even head loss. Okay, we can use that to determine the pressure difference, to determine the velocity, things like that. So comparisons of two the Bernoulli equations that has been used to compare between 2 points is a very useful approach. Alright, so if you are interested in the derivation, you can look into this diagram and also the steps given here. Then you should understand how this Bernoulli equation is actually being derived. Alright, and here, but basically, if you look here, basically there are how to say it, it's basically the balance of forces. Okay, you have a bottom force and upper force, which is based on the pressure force, and then you have this gravitational force that is pulling down. So you can what I call it, separate it into two forces. One that is normal to the fluid in red, and one that is in the same directions of the pressure force. All right, And then of course there's another one that is the moving of the fluid. Okay, the moving of the fluid, that's why you have this ma. Okay, so this is, if you look properly, here is actually the force F equals to m, and then this v dv ds is actually the a, okay, the acceleration, all right, of this fluid in red color. All right, so the sum of kinetic potential and flow energies of the fluid is constant along the streamline. So here the red line, the blue line is actually the streamline. So in the streamline, you might have a change of kinetic, change of potential, change of flow, but the sum of these three, the sum of kinetic, potential, and flow along this blue line, the streamline, is always constant. Okay, during steady flow, when compressible and frictional loss are negligible. All right. So one more point to add into this slide is that here we have this what I call compressible flow and steady flow. Okay, then of course we have this steady and incompressible flow. So that's why here we see the steady flow, compressible. You can see that there is a change of density with pressure. All right. So this slide shows the steady flow along streamline with compressible flow, and then the second equation here shows the incompressible flow, also steady flow. Right, so the incompressible Bernoulli equation is derived assuming incompressible flow, so it should not be used for flow with significant compressibility effect. All right, so let's say you have changes of density with space, okay, with different location. Therefore, this equation is not applicable. You might want to consider using this equation. But most of the case that we discuss in this subject, we use incompressible flow. So the case of this equation is not much of concern. So we will limit our discussion most of the time to this incompressible steady flow equation. Right? All right. Repeat again. The Bernoulli equation states that the sum of kinetic potential and flow energy of fluid particles is constant along streamline during steady flow. So the energy might change from one form to another, but the total sum of this what we call mechanical energy, okay, is always the same. The total sum is constant, and we can view this Bernoulli equation as a conservation of mechanical energy principle. Okay, and they do not involve any conversion of mechanical energy and thermal energy to each other. Means they are mechanical energy, they are conserved to mechanical energy. They do not change to thermal energy, and the mechanical energy and thermal energy are conserved separately. So mechanical energy will stay as in the forms of mechanical energy, means flow energy, kinetic energy, and potential energy. They can only interchange between one another, but they cannot change to thermal energy. Okay, because thermal energy involve another process. So these are the general conservation energy principle. Okay, so the Bernoulli equation state that during steady incompressible flow with negligible friction, various forms of mechanical energy are converted to each other, but their sum remain constant. Means total is always the same, but they can change to one another. There is no dissipation of mechanical energy during flow, since there is no friction that convert mechanical energy to sensible thermal internal energy. Means that there's no heat loss. All right, okay, there's no loss. There's no conversion of, let's say for example, flow energy into heat energy, or kinetic energy into heat energy, or potential energy into heat energy. There is no such conversion. There is only interchangeable between three of these mechanical energy. Right, so that's why there's no friction, there's no mechanical, there's no sensible thermal internal energy loss. Okay, so Bernoulli equation is commonly used in practice, since a variety of practical flow problem can be analyzed to reasonable accuracy with it. So in many previous slides, I showed to you the applications of Bernoulli equation. Alright, so that's how Bernoulli equations are being used to solve many practical problems, because they are quite reliable in many of the cases that we just described. In the previous slide, I showed to you there is the static pressure, there is a dynamic pressure, and also hydrostatic pressure. So other words for static pressure, you can also call it as a stagnation pressure. So when we talk about stagnation pressure,
we are interested at a point where the fluid actually stop moving. Okay, so how does that work? For example, if you design a tube and then you make two tube. One tube is made of piezometer. Piezometer is just to make a hole into a pipe and allow the fluid to rise to a certain height based on the pressure within the tube. And then we make another tube, we call it pitot tube. It is bent in the middle of the pipe, where the pipe is bent in an L shape, where the tip of the hole of the pipe would face the direction of the incoming fluid. So what happens is that when the fluid is coming from, let's say, from point 1 to point 2, when the fluid was at point 1, it moved at velocity v. When it reaches the point 2, the velocity becomes 0. So v1, you have a velocity v. v2, the velocity is 0. So that is the point where we call it stagnation. Okay, stagnation pressure hole. Okay, if you look into diagram, this diagram showed you this is this figure showed you this stagnation pressure hole. All right, of course there's also some other things being there is a static pressure hole that built around this pitot tube, but the main point here is that we want to show you that there's a point in the pitot tube which face the incoming fluid. So when the fluid comes, it hit the stagnation pressure hole, the fluid will come into stop. So when that happens, what happens is that this velocity, the dynamic pressure, will be fully converted into static pressure, or we call it stagnation pressure. All right, stagnation pressure. Okay, now we look at this stagnation pressure, the sum of static and dynamic pressure. Okay, so you have a static pressure, and then you have a dynamic pressure. Both of them sum up and give you a stagnation pressure. It represents the pressure at the point where fluid is brought to a complete stop isentropically. Isentropically basically means that there is no transfer of heat, there's no transfer of mass. It's basically just means that the fluid just come to a stop without any additional mass or loss of mass. Okay, that's what it means. So the easiest way to understand this is that we look back into the what I call the Bernoulli equation. Alright, so we can write a Bernoulli equation to compare at the point where the fluid is moving, and also compare to a point where the fluids come to a stop. Alright, so we make a Bernoulli equation for point 1 and point 2. So when we compare point 1 and point 2, you can see that at point 1 and point 2, they are basically at the same elevation. So the Z1 and Z2 can be cancelled out. And then we also realize that at point 2, the fluid will come to a stop. Therefore, the velocity will be cancelled out as well, because the velocity V2 will be 0. So we only left with P1, V1, and P2, right? So if we rewrite this equation, we will get V1 equals to this formula. Alright, so what's interesting about this formula is that when you design a pitot tube, inside this pipe, with the presence of a piezometer, and you can find there's a difference of height of water, the liquid level between this pitot tube and also this piezometer. So the difference height is actually V squared over 2G. So it's basically, if you simplify this equation, you will get V1 squared over 2G. Okay, so that's basically the height, and this formula allow us to determine the velocity. Okay, the velocity of the incoming fluid. All right, so without needing a meter, we just look at the difference of water height, the liquid height, so we can determine the velocity of the moving fluid. Also, this kind of tube is called pitot. Okay, pitot static probe. Okay, so a close-up of a pitot static probe showing the stagnation pressure hole. Okay, so we have a stagnation pressure hole, and 2 of the 5 static circumferential pressure holes. So we have
2 holes here. Actually, there are 5 holes surrounding this pitot static prop. All right. And there's the static, dynamic, and stagnation pressure. Okay. Measure using piezometer tube. Okay. Here we have 2 figures. So at the top we have a figure showing that where you place the piezometer in the pipe is also important. So make sure you avoid near the sedimentation. So careless drilling of static pressure tap may result in an erroneous reading of a static pressure head. So you want to pick the location here, which is far away from the ending sedimentation. So if you nearby there is a sedimentation, for example, if you place the piezometer tube before sedimentation, you get higher pressure. If you place it after the sedimentation, you get a lower pressure. So if you place it nowhere near any sedimentation, you get a correct value that is in between this high and low. Alright, so our objective is to find this place where there's no sedimentation. Right, so how do you know? So you need to find a few spot in the pipe, then only you know which place is safe to is most likely to give a correct reading, right? And of course, this kind of thing will only come to you through what I call experience. So if you can use some kind of sensor, some kind of imaging that can actually see through the pipe, then you can see clearly where you want to place in the piezometer. Otherwise, you will have to do some kind of guessing work. Alright. And then this figure below show you this straight line produced by a color fluid introduced upstream. So here is a airfoil. So you have an incoming fluid, okay, but it is color, so that they can actually capture with some kind of camera. You can see the flow of the dye, some kind of color fluid through the airfoil. Since the flow is steady, the straight line are the same as a streamline and a path line. So the stagnation streamline is marked. Okay, so this is a stagnation streamline. So it comes and stop at the peak of the airfoil. So that is a distinction between straight line, streamline, and path line. Okay, so path line is the easiest way to imagine path line. Is like, for example, if you throw a stone, then you could imagine that the path taken by the stone from the beginning, you throw from the point you throw it to the point stop. So that is a path line. So we have a path line for the fluid flow, and then of course we have a straight line. Straight line is like if you throw the stone, imagine that the stone leave some residue behind, and then what happens if the wind changes with time, so the residue that left behind by the stone will also changes direction with time. So that's how streamline difference from the path line. Path line is just referring to one stone, and streamline referring to the past history of the path taken by the stone. Another way to look into straight line is that if you inject the ink into the river, so if the river flow in the steady state, then the path line and the straight line will be the same. But if the velocity in the river changes direction with time, therefore the path line will only look into the initial point where the first dye actually enter the river, but the straight line will show you how this dye will actually change direction as the velocity in the river changes. Okay, and streamline is basically referring to the how we call that, the tangent of the stream. So the velocity, the tangent velocity of the stream flow. Okay, so that's basically the distinction between straight line, streamline, and path line. So these are not important when you are in a steady flow, because straight line will be the same as streamline and path line. Okay. So here we look at limitations on the use of Bernoulli equation. So in a Bernoulli equation, the first limitation is a steady flow. So Bernoulli equation is applicable to steady flow only, okay. And then second, frictionless flow. Every flow involves some friction, no matter how small, and a frictional effect may or may not be negligible. So this is a second limitation. The third limitation is no shaft work. The Bernoulli equation is not applicable in a flow section that involve pump, turbine, fan, or any other machine or impeller, since such devices destroy the streamline and carry out energy interaction with fluid particles. So when these devices exist, the energy equation should be used instead. Okay. In compressible flow, the density is taken constant in the derivations of Bernoulli equation. The flow is incompressible for liquid and also by gases at much number less than about 0.3. So Bernoulli equation is only applicable for incompressible flow. So if it's incompressible flow, the flow energy equation, you have to do some kind of some form of integration, okay. And then no heat transfer. The density of a gas is inversely proportional to temperature. Alright, and thus the Bernoulli equation should not be used for flow section that involve significant temperature changes such as heating and cooling section. So we assume that the temperature in the medium that we are looking at has a homogeneous temperature. Alright, flow along a streamline. Strictly speaking, Bernoulli equation is applicable along a streamline. However, when a region of flow is irrotational and there is negligible small vorticity in the flow field, the Bernoulli equation become applicable across streamline as well. Alright, so basically Bernoulli equation is only applicable in the streamline. Okay. This slide shows the condition where Bernoulli equation becomes inapplicable. Okay, so it means all these conditions shows when the Bernoulli equation fail. Alright, so the here you can show that there is a sudden expansion. Okay, so sudden expansion is also an issue, so it will make the Bernoulli equation fail. The other one is a long narrow tube. So this long narrow tube, the problem with this long narrow tube is that we have too much friction, right? And then the other one is a fan. If you use fan, it will break the streamline. As we know, Bernoulli equation is only applicable in the same streamline. So this case will break the streamline. Therefore, the Bernoulli equation may not be applicable. And then the other one is a heating. So if you have a heating in a fluid flow system, therefore the temperature is no longer homogeneous. As a result, Bernoulli equation may not be applicable because you are introducing energy into the system that cannot be accounted by the Bernoulli equation. Right. And the other one is a flow through a valve. Okay, so flow through a valve also something the same as this case. Like for example, this case is sudden expansion, and this case is a sudden contraction. Okay, so we have a similar problem. Contraction or expansion also will make the Bernoulli equation fail. And then the other one is a friction region. So we have a viscous layer. For example, this is airfoil. The fluid flow over the top and bottom of the airfoil. As a result, we develop a region we call boundary layer near the airfoil, and also the wake region at the back. So this is the viscous region. Okay, viscous region. And then outside of this viscous region, we have an inviscid region. So the Bernoulli equation is only applicable outside the viscous region. Alright, so this is another limitation. If you want to apply the Bernoulli equation within the viscous region, then the Bernoulli equation would fail. Alright, so frictional effects, heat transfer, and components that disturb the streamline structure of flow makes the Bernoulli equation invalid. So it should not be used in any of the flows shown here. Okay, and then of course when we want to use it across streamline, it is applicable only when the flow is irrotational. Bernoulli equation become applicable between any 2 points along the flow, not just on the same streamline. So which means that if you want to use it across streamline, it is applicable as long as the fluid is irrotational. That is the most important point. Alright, then this Bernoulli equation becomes applicable. Okay, means there is no break of streamline. So here I would like to introduce to you another forms of what we call Bernoulli equation. Alright, so we have here is hydraulic grade line HGL and energy grade line EGL. So this part, the following section, we will talk about HGL and EGL. Alright, before we do that, let's look into these another forms of Bernoulli equation. It is often convenient to represent the level of mechanical energy graphically using height. Okay, so instead of using pressure, energy, things like that. So now we want to represent these terms of Bernoulli equation using height, using meter, okay, elevation. Alright, using height to facilitate visualization of various terms of Bernoulli equation. So dividing each terms of the Bernoulli equation by g, means g is a gravity, give these forms of equation. Okay, so this is the forms of Bernoulli equation that I've been using a lot. I'm showing to you in many previous slides. So it's the same thing. We have a pressure head, okay, pressure head. We have a velocity head, okay, velocity head, and then we have an elevation head, okay. And then you combine all this head, you get a total we call it total head, okay, total head also. So this is a figure show to you that we have a pressure head, velocity head, and also elevation head, okay, and combine to give a total head which is constant. All right, if you follow the same streamline, okay, if you compare the energy between one point to another on the same streamline. So let's say you compare point 1 to point 2 on the same streamline, therefore you get the same total head. That's what it's trying to say, the constant here. Okay, the constant means that the energy at the same streamline at different point is the same. All right, and alternative forms of the Bernoulli equation is expressed in terms of head. So this is alternative forms of Bernoulli equation. The sum of the pressure, velocity, and elevation heads is constant along a streamline. So the same streamline, you have the same total head, okay, which is, we can consider it as a constant. All right. So here is the hydraulic grid line and energy grid line explanation. Here also include additional explanation for the dynamic head. So the dynamic head is given by v squared over 2g. All right. So the hydraulic grid line, in short, we call it HGL, and then we have this energy grid line, in short we call it EGL. Right. So hydraulic grid line include this pressure head and elevation head. Whereas for this energy grid line, it includes everything. Okay, pressure, velocity, and elevation. Okay. So if you look here into this figure, this figure shows the hydraulic grid line HGL and energy grid line EGL for free discharge from a reservoir through a horizontal pipe with a diffuser. So you have here a diffuser. Diffuser basically means you from a confined area to a more greater area. So you have a diffuser. All right. So the amount of mass flow rate flowing through this pipe is the same. All right. So the same mass flowing through this pipe. So you can imagine that a small area, a small diameter area, the fluid will be flowing through faster, and for a large diameter area, the fluid will flowing through slower. Okay. So as a result, you could expect high speed here and low speed in a larger area. So you can see that here we have in different parts of the pipe, we have this piezometer as well as pitot tube. Okay, so both this piezometer and pitot tube combines to form this to form the measurement unit for velocity. Okay, because you have here this is a point where the stagnation happen. When the fluid comes in contact with this point, the fluid will stop. So all this pressure, this kinetic energy will be converted into the water height. Okay, so we can actually separate out the kinetic, okay, from the total head. Okay, so that's why we have this HGL, which include only pressure and elevation, and then we have an energy grid line, which is the EGL, which combine pressure, velocity, and elevation. So as a result of having this unit, we can estimate this velocity head, and then we separate it from the energy grid line. So energy grid line is the top here at the top. So you can see here this solid line is an energy grid line, and then at the dashed line below is a hydraulic grid line. So hydraulic grid line only have two forms of head, is a pressure head and elevation head. And for energy grid line, it include another one that is the dynamic head or the velocity head. Okay, so overall you can see the head drop with distance from the reservoir. So this is because of the friction loss. Okay, friction loss, the major and the minor loss. Okay, so it's due to friction. So overall the total head drop, or the EGL drop, the energy grid line drop. But not only that, the hydraulic grid line also drop. And one of the interesting thing you can see here is that the velocity estimated within the diffuser is actually higher. Before the diffuser is actually higher, and then after the diffuser is actually smaller. So the velocity here is larger than the velocity near the exit point. Why? Because in near the diffuser, before the diffuser, the speed is faster. Okay, so more kinetic energy. So more kinetic energy converted can be actually captured. So we have more what I call dynamic or velocity head. But in the after the diffuser, so the fluid flow as flow in a lower velocity. So lower velocity, you also will capture lower velocity head or dynamic head. Okay. Here are some notes on HGL, hydraulic grid line, and EGL, energy grid line. Okay, so for stationary bodies such as reservoirs or lake, the EGL and HGL coincide with the free surface of the liquid. So for example, if you look here, stationary bodies such as reservoir and lake. So here's a reservoir or lake. So you have this EGL and HGL coincide with the free surface. Okay, then the EGL is always a distant. Okay, always a distant V square over RG above HGL. The two curves approach each other as the velocity decreases, and they diverge as the velocity increases. So if you look here, the EGL is always above HGL, right? And is separated by the distance V square over RG. So if the velocity is big, then they are far apart. But if the velocity is small, they are closer to one another. In an idealized Bernoulli type flow, EGL is horizontal and its height remain constant. So for the case of idealized Bernoulli type flow, so the EGL is always horizontal, but we have a HGL that changes according to the difference of velocity. So in the idealized Bernoulli case, so the EGL will be horizontal. Alright. So for open channel flow, HGL coincide with the free surface of the liquid, and the EGL is a distant V square over RG above the free surface. This one we talk about. At a pipe exit, the pressure head is 0 atmospheric pressure, and thus the HGL coincide with the pipe outlet. Okay, so as a fluid flow outside, so the HGL, the HGL line will coincide with the pipe outlet. Okay, so HGL will coincide with the pipe outlet as shown in this figure. So the mechanical energy loss due to frictional effect conversion to thermal energy causes the EGL and HGL to slope downward in the directions of flow. The slope is a measure of the head loss in the pipe, a component such as valve that generates significant frictional effect. causes a sudden drop in EGL and HGL at that location. So you see that we have a EGL and HGL drop with space. So this drop is the result of head loss, okay, result of fictional loss inside the pipe. We call it major or minor losses in the pipe. Okay. A steep jump or drop occurs in EGL and HGL whenever mechanical energy is added or removed from the fluid. So if you use a pump, we can see if you use a pump, we can see a steep increase. If we use a turbine, we can see a steep decline. Alright. So EGL and HGL respond to the types of mechanical device that install into the flow system. Okay, and the last one, the gauge pressure of a fluid is 0 at location where the HGL intersect the fluid. Okay, the pressure in a flow section that lies above the HGL is negative. Okay, so so you can see the fluid that lies above the HGL line, they are negative. Alright, and then below it is its positive pressure. So as stated here, the flow in the pressure in the flow section that lies above HGL is negative, and the pressure in the section that lies below the HGL is positive. Okay, so you can see that you have negative pressure above and positive pressure below. Right, so this figure shows the gauge pressure of a fluid is 0 at location where the HGL intersect the fluid. So the HGL intersect the fluid, okay, and the pressure is negative vacuum in the flow section that lies above the HGL. So when it lies above the HGL, you got negative pressure. Below it, you get positive pressure. And this figure here shows when you put a pump, you increase the energy in the system, so you increase the EGL as well as the HGL. But then if you put a turbine, you can see a steep decline. So you have a steep increase because of pump and a steep decline because of turbine. So what's the difference between pump and turbine is that pump input energy into the system and turbine extract energy from the system. So here we have two examples using Bernoulli equation. So we look at the first example, water discharge from a large tank. So what happened is that we can compare point 1 with point 2. Point 1 is at the top of the water in the reservoir, and point 2 is the exit of water through the bottom of the through the side bottom of the tank. So if we write out the Bernoulli equation, what we can see is that we could basically see that the pressure at P1 and the pressure at P2 they are at atmospheric pressure. So basically they are the same, so P1 and P2 can be cancelled out. And then since this is a surface of water, so in the reservoir, the free surface, the water movement is very slow, means that the velocity is very slow. So V1 is equal to 0, near 0, and V2 is not 0, so they've got some value on V2. Alright, and then we have a Z1 and Z2. So if we pick Z2 as a reference point, so Z1 minus Z2 will be equal to 5 meter. So in this case, we know we can assume Z2 as 0. Then we know Z1 is 5 meter above water. So in this case, we set the Z2 as 0. Then we know this Z1 should be 5 meter. So in this case, we cancel out Z2. We make Z2 as 0. So what we have here is we have Z1, we have V2. Okay, so we can write this equation as Z1 equals to V2 square over 2G. So we know that Z1 is 5 meter, then we can actually estimate what's the value for V2. Alright, so that's the first example. In the second example, we look at spraying water into the air. So this boy is holding a hose and then using his hand to stop the water from flowing out completely. So in this case, he can allow the water to speed as it exits from the hose. okay, from the water jet. So the water jet, it basically go upward into the air, open air, and then as it reaches the maximum point where the water could go up, it will just stop and falling down from a certain height. All right. So in this case, we write a Bernoulli equation comparing the water within the hose, the water hose, and then comparing at the location 2 where the water basically hit the top before it stopped moving and falling down. So in this case, it's quite obvious that the velocity v2 equals to 0 because it stopped, and then z1 is used as a reference point, so z1 becomes 0, and then z2 is an elevation, is a maximum point 2 from z1. So basically we can know how high the water will actually go, because we can see how high the water actually go up. So we got z2 has some value, z1 equals to 0, and then p1 and p2. So in this case, we can look into here. P1, we know that because the boy use a finger to close a portion of the cross-section area, which try to restrict the water from going up. So the pressure is building up within the pipe. So we have some value, some pressure, P1, and then at P2, we know that P2 will be at atmospheric pressure. Okay, so if we ignore atmospheric pressure, then P2 will be 0, and then P1 is only gauge pressure. But if we include the atmospheric pressure, then P2 will be atmospheric pressure, and then P1 will be gauge pressure plus atmospheric pressure. So in this case, they show that they include the atmospheric pressure with gauge pressure. So the P2 become atmospheric pressure, and the P1 become gauge pressure plus atmospheric pressure. All right. So and then Z1 is 0, and then V1 is near 0, because why? Because the water moving up slowly, okay, and a lot of water is kept within the hose. So V1 almost 0, and V2 of course is 0 because the water will stop at the top. So V1 0, V2 0. So we only left with P1, P2, and Z2. That's how we get this equation. Here is another example. This example shows siphoning out gasoline from a fuel tank. So we have, as you shown in this figure, there is a 3 point being labeled, point 1, point 2, and point 3. So what happens is that we withdraw the gasoline from gas tank to the gas can. Alright, so we have 3 points. First, we compare point 1 with point 2, so point 1 with point 2, and then the second one we compare point 2 with point 3. So the significance of this example is that you can see that when we compare different points, we will get different information. For example, when we compare point 1 with point 2, we get to estimate the velocity at point 2 that flowing out. And then when we compare point 2 with point 3, we get the information. We can estimate the pressure at point 3. Okay, so these are the information we can get. So let's look at the example that we compare point 1 with point 2. So we write the equation for Bernoulli equation for point 1 equals with the Bernoulli equation for point 2. So what happens is that initially we look at that we have a free surface here. So with the velocity will be 0, V1 will be 0, and then we have a velocity flowing out from the pipe, so we have V2, and then since point 1 and point 2 they are exposed to the atmosphere, so they are exposed to the atmosphere, so basically P1 and P2 can be cancelled out. Okay, so we have V2 and but V1 0, P1 0, and P1 equals to P2, so both become cancelled out, so we cancel out P1 and P2, and then now we have Z1 and Z2. So if we could use Z2 as a reference point, then Z2 can be cancelled out, and then we only left with Z1. So our equation can be simplified to Z1 equals to V2 square over RG. So this comparison allow us to have this equation, which then can be used to estimate the velocity at point 2. Then now if we compare point 2 with point 3, so we write Bernoulli equation for point 2 compared with Bernoulli equation at point 3. So in this case we can see that okay, what can we say that is that the velocity of V3 and V2, they are the same. Okay, the velocity flow inside the pipe and the velocity exit the pipe is the same. So V2 and V3 can be cancelled out, and then if we can use Z2 as a reference point, then Z2 becomes 0. Then we only left with Z3. But when it comes to pressure, we can say that the pressure inside the point 3, in the point 3 you have gauge pressure as well as atmospheric pressure, whereas at point 2 you only have atmospheric pressure. So if we maintain the pressure here for atmospheric, if we include the atmospheric pressure, therefore for P2 we become atmospheric pressure, and for P3 we get gauge pressure plus atmospheric pressure. Alright, so this is the equation we get. So at the end of comparing point 2 with point 3 is that we get to estimate the pressure in the point 3. Okay, so in this example it shows the velocity measurement by a pitot tube. So here we have a piezometer tube as well as pitot tube, and some value is given here, H1, H2 and H3, different height between different height that shown here. Alright, so we compare point 1 and point 2. So point 1 is referring to the point below the piezometer, and then point 2 referring to the stagnation point of a pitot tube. So when we compare point 1 and point 2, we just write the Bernoulli equation for point 1 equals to the Bernoulli equation for point 2. So what happens is that you can see at P1 you have some pressure, P2 you also have some pressure. So P1 and P2 is present in the equation, and then V1 and V2, what happens is that V1 you have the water that is moving, and V2 we have the water that stops. Okay, the water becomes stagnation. So as a result V2 becomes 0. So you only have V1, and then Z1, Z2 is that both of them in the same elevation. So Z1 equals to Z2. As a result, Z1 is cancelled out, Z2 is also cancelled. Alright, so basically we only left with V1 square over R over 2G equals to P2 minus P1 divided by rho G. So P1 is given by the height of water, the pressure given by the water above it. So in this case P1 equals to rho G in the bracket H1 plus H2. So for P2 will be given by the pressure of the liquid above it. So this pressure is equals to P2 pressure is equals to rho G in the bracket H1 plus H2 plus H3 in the close bracket. Okay, that's how we get to estimate the velocity of the water in the pipe. So here is an example of the rise of the ocean due to a hurricane. So the eye of Hurricane Linda in 1997 in the Pacific Ocean near Baja, California, is clearly visible in this satellite photo. So we're trying to use a Bernoulli equation to explain this hurricane formation, not formation but hurricane phenomena. Alright, so what we do here, we want to use the Bernoulli equation to represent the pressure, velocity and elevation for the 2 points. One is the point at B, which referring to the eye, and then the other point is some distance away from the eye, which referring to the point A. So what you can see is that we wrote this equation for point A and point B for Bernoulli equation, and then we can make some comparison. So obviously you can see here ZA and ZB has been cancelled out, so there is a difference of height of water but very small. So in this case we can actually cancel it out. Alright, and then maybe it's not very obvious to you, but those who are familiar with the hurricane is that in the eye there's basically no movement of air. So the air in the eye actually stops whereas the air surrounding the eye is moving fast, right? So in this case, VB becomes 0 and VA is present. And then the pressure, of course, there is some pressure difference between point A and point B. So in the end, we get the equation of pressure B minus pressure A over rho G equals to VA square over 2G. So these are the equations that can be used to represent this phenomena. Now let us look into the general energy equation. So according to the first law of thermodynamics, the conservation of energy principle, energy cannot be created nor destroyed during a process. It can only change form, right? So if you put certain amount of energy and take out certain amount of energy, then you have a change of energy in the system. So the energy we're talking about is always in the unit of joule. When we develop the joule with time, you will get watts. Okay, so to have a better understanding of the energy system, so imagine that here the energy change of a system during a process is equal to the net work and heat transfer between the system and its surrounding. So you have a certain amount of heat entering the system, let's say 15 kilojoule entering the system, then we have a 3 kilojoule flowing out of the system in the forms of heat, and then you have a shaft that provide 6 kilojoule of work, rate of work, energy into the system. Then you can basically estimate the energy within the system. So you have a 15 input minus 3 and then plus 6 kilojoule from the shaft work, then you have a total of 18 kilojoule of energy given to the system. Alright, so as I said, the changes of E, changes of energy is in the joule, and then if you take the joule divided by time, and then you get watts. Okay, so the changes of energy in the system means the changes of energy in the system divided by time. The rate of energy change in the system is equals to the the heat, the net heat, and the net heat transfer to the system, and the net work done to the system. Alright, so the changes of energy in the system with time, we can convert it into this form. So we have a rho density of a fluid, for example. E is the energy that given by joule per kilogram. Okay, and then dV is the changes of volume. Alright, and then dt, of course, is the changes of time. So if you calculate the whole term, you get the unit of watts. Okay, so Q net in is the Q in minus Q out, the heat transfer in or out from the system. The W net in is equals to W and the work entering the system or the work taken out from the system, and the E itself is given by the internal energy plus kinetic energy plus potential energy. So internal energy, kinetic energy, and potential energy. Alright, energy transfer by heat Q. Thermal energy, there are two: sensible and latent forms of internal energy. Sensible heat involve transfer of energy in the forms of difference of temperature, and the latent forms involve phase transition, for example from liquid to become vapor. So that is a latent forms of energy. Heat transfer, the transfer of energy from one system to another as a result of temperature difference. So when there is a temperature difference, there is a transfer of energy. The directions of heat transfer is always from high temperature body to low temperature body. So have high temperature to low temperature. That's how the heat transfer have happened. Adiabatic process is a process during which there is no heat transfer, and heat transfer rate is a time rate of heat transfer. So basically, heat transfer rate is referring to watt. So heat itself is joule, and the rate of heat transfer is joule per second, joule per time. So you get watts. Okay, so the time rate of heat transfer is watt. Okay, the temperature here, this figure shows the temperature difference is driving the force for heat transfer. The larger the temperature difference, the higher the rate of heat transfer. So this example, it shows that when the soda can is 25 degrees Celsius, when the room temperature is also 25 degrees Celsius, therefore no heat transfer. When the soda can is 15 degrees Celsius, therefore the room is 25 degrees Celsius, therefore we have a heat transfer into the can from the room temperature. So if the soda can is even colder, you will get even more heat transfer into the soda can. Okay, so the heat transfer is basically based on the difference of temperature. Here we look at energy transfer by work, W. So work, the energy transfer associated with a force acting through a distance. So you have a force, Newton, and then force acting through a distance, then you have a meter. So Newton multiplied with meter, you get joule, W, which is the unit. You have a unit for work is joule. So for example, a rising piston, a rotating shaft, and electric wire crossing the boundaries, the system boundaries, are all associated with work interactions. Power is the time rate of doing work. So if we take the work, which is in the unit of joule, divided by the time of doing the work, then you get the unit of watts. Okay, for example, car engines, hydraulics, steam, gas turbine produce work, compressor, pump, fan, and mixer consume work. So if you take into account of the total work is given by the work done by shaft plus the work done by pressure plus the work done by viscous and plus the work done by other forces. Okay, so the work done by viscous basically means the viscous of the fluid. Okay, the viscous of the fluid that causes the work done. Alright, so W shaft, the work transmitted by a rotating shaft. W pressure, the work done by the pressure force acting on the control surface. And W viscous is the work done by normal and shear components of viscous forces on control surface. And W others, the work done by other forces such as electric, magnetic, and surface tension. So without going too much details into the work, I will just skip the work, shaft work, so you can look into this if you are interested, and also the work done by pressure forces. I also will skip this, and the most important thing that this whole thing is to point out that we have a control volume. Alright, okay, the control volume contain the mass as well as the energy. Alright, and this within the control volume have incoming mass and also outgoing mass. So you have a mass entering the system as well as the mass leaving the system. So the CV referring to the control volume, the store of mass, the store of energy in the system, and then this mass can also entering the system, can also leaving the system. That's why you have a control surface, so entering and leaving. So apart from mass movement, if there is no mass movement, we also will have this energy transfer, heat transfer. Okay, so heat can actually entering the system. Okay, the Q net in. Okay, and also the work done to the system. You get shaft work as well as a pressure work in the system. Alright, so on the left side, you account for the what we say the heat transferring into the system, or the heat transferring out from the system. We also account for the work done by the shaft as well as the work done by the pressure in and out. And then on the right side, we have the conservation for the energy in the system that account for the mass storage in the system. So the energy account for account for the storage in the control volume, and then you have a mass inflow and outflow from the system. Alright, so that's basically what it means for the whole this equation. So without going in too much detail into this derivation process, but you can look into that if you're interested. So basically you have a net rate of energy transfer into the control volume by the heat and work. Okay, so basically these three terms are referring to this bracket, and then equals to the this term control volume is the time rate of change of the energy content of the control volume. Okay, then plus this the net flow rate of energy out of the control surface by mass flow. So this basically means the the net flow rate of energy out of the system by mass flow rate. So the mass flow carries the energy. That's what it means. So the mass flow can also enter the system, can also leave the system. Okay, so if you understand this statement here, basically you understand the equation that described here. Okay, so without giving too much details into the derivation, but of course if you are interested, you can always go through the derivation process, the derivation details. You can always ask me for these details if you are really interested into the derivation process. Alright, otherwise we will go straight to the point. So what the system is going to point out to you is that you can see that throughout the whole derivation process, you will come to the realization that you have the Bernoulli equation that you can compare at two different points, point 1 and point 2, and then you have this H pump that's located in the left side of the equation, and then you have the H turbine that is located on the right side of the equation, as well as a HL. So the HL is basically the head loss. Okay, head loss account for the major loss as well as the minor loss. So this loss is because of the piping system. Okay, piping system. Alright, so why do we have a H pump? H pump is the energy that is the head that provided to the fluid system, and H turbine is the energy that taken out from the fluid system. And similarly, HL is also taken out energy from the system, but this H loss is actually referring to the minor loss and major loss. For example, friction in the pipe. So these are the head loss. Okay, HL. Sudden contraction or expansion in the pipe, that is also this H loss. Okay, HL, H loss. So again, we referring back to the same equation that has Bernoulli equation, has a H pump, has H turbine, and a head loss. So this diagram summarizes this equation. So what can you see is that we compare 2 points, point 1 and point 2. So we have energy at point 1 and then energy at point 2. So the height of this vertical height is referring to the column height of fluids. Okay, so it's a vertical dimension, shows the energy terms expressed as an equivalent column height of fluid in head. So basically in the meter. Okay, so the longer the length, the higher the energy amount. So this is a combination of what you call pressure head, velocity head, and elevation head. Okay, so this you have this energy given in point 1, and then if you have a pump, the pump will provide energy into the system. Alright, and then it will be equal to the point 2 where you still have the energy, and the energy in the point 2, if you have a turbine, some energy will be taken up by the turbine, and then because the fluid will flow through the system, let's say a piping system, there will be a joint, a valve, a pump, a contraction, expansion of the pipe, turning of the pipe. All this will cause the head loss. Okay, so the head loss will take certain amount of energy out from the system. So this diagram summarizes the whole this whole line of equation. So we have energy Bernoulli equation, energy for point 1 and point 2, and then you have a H pump that add energy to the system. You have a H turbine that take energy out from the system. Similarly, the head loss also take the energy out from the system. So this diagram shows the mechanical energy flow chart for a fluid flow system that involve a pump and a turbine. Okay, these slides again we referring to the same equation. Alright, so this is the energy equation that if you remember that there's steps involved in the derivation of this equation. So in a special case, for example, in an incompressible flow with no mechanical work devices and negligible friction. So if you hear the word negligible friction, means no heat loss. So heat loss becomes zero. No mechanical work devices means H pump, H turbine cancel out. So if that's the case, no H pump, no H turbine, and no heat loss, therefore you will return back to the Bernoulli equation. So Bernoulli equation, this is exactly how it looks like. So this is the Bernoulli equation derived earlier using Newton's second laws of motion. Right? Thus, Bernoulli equation can be taught as a degenerate forms of energy equation. So this is an energy equation. So when you assume no mechanical device, no mechanical work devices, and negligible friction, therefore you end up with Bernoulli equation. Okay, so these slides show to you there is a kinetic energy correction factor alpha. Alright, so if you look at this energy equation, you can see that everything is the same except that we have one alpha 1 and alpha 2. So this alpha 1 and alpha 2 are introduced as a correction to the equation. Why? Because when we compare the kinetic energy actual with the kinetic energy average, we found out that this alpha, this ratio is actually greater than 1. So you get about 2.0 for fully developed laminar pipe and 1.04 to 1.1 for fully developed turbulence flow in a round pipe. Alright, so that's why we need to have a correction alpha 1 and alpha 2 in the energy equation. Alright, so this correction is necessary if you want your estimation to be accurate. Okay, so we are looking into this example 512, the pumping power and frictional heating in a pump. Okay, so the pump of a water distribution system is powered by 15 kilowatt electric motor. So you have energy. We have energy. Hold on. We have energy given by the electricity. Okay, to power the how to say, to power the motor. Okay, so this is electric power. All right, electric power 15 kilowatt. You can also write it as 15,000 watt. Okay, 15,000 watt. And then you have the whose efficiency. Okay, efficiency is 90%. Okay, so we know it's 15 kilowatt electricity. Okay, and then the efficiency is 90%. Okay, as shown here, it is 90% efficiency. So the efficiency of motor is 0.9%. Okay, it's 90% but 0.9 in terms of fraction. And the water flow rate through the mass, the water flow rate through the pump is this much. Okay, water flow rate is the volumetric flow rate. Okay, 50 liter per second, which is 0.05 meter cube per second. Alright, and the diameter of inlet and outlet pipe are the same. So here, the diameter here and the diameter here, they are the same. Alright, so D1 equals to D2. So the implication of having this is that V1 will be equals to V2. Right, same diameter, same flow rate. Same diameter, same velocity. Alright. Okay.
and the elevation difference across the pump is negligible. Okay, so what does it mean? It means that Z1 equals to Z2. Alright, if means the difference between this point and this point, the difference of a height is negligible. Okay, small. Okay, if the absolute pressure in the inlet and outlet of the pump are measured to be 100 kilopascal and 300 pascal, so the inlet and the outlet of the pump, the pressure 100 and 300. Okay, so you can write down here as P1 P1 is 100 kilopascal, or okay, right, P2 300 kilopascal. Oh, okay, so it's a very huge pressure. And A, so you are asked to find A, the mechanical efficiency of the pump. Okay, you are asked to find the mechanical efficiency of the pump. So you see, this motor take in some electricity, which is 15 kilowatt, and then it convert to the shaft work, and then from the shaft work it convert the energy to give it to the water, so the water will absorb the energy from the pump. Alright, so 15 kilometer, 90% of 15 kilometer convert to shaft work, and some portion of the energy is given to the water. So we need to find what is the efficiency of the conversion. Alright, that's why we need to find the efficiency of the pump. So how do we know? So we try to compare. Okay, we try to compare the different point from point 1 to point 2. So, and then we can know how much energy is actually absorbed by the water, the energy that being given by pump to the water. So we do what we do, we write down the equation for this energy equation. Okay, so since there's a H pump, so we must have H pump. Okay, P2 4G, V2 2G, Z1. So what can we see from here is that we know that Z1 Z2 is cancelled out. Okay, and we also know that the velocity is the same because same diameter, also cancel out. Alright, so we left with P1, P2 and H pump. Okay, P1, P2 and H pump. So H pump equals to P2 minus P1 rho G. Alright, and then we need to find the watt power. Okay, for pump. So we need this one. It allows us to estimate how much energy that is given to the water by the pump. Okay, so we multiply with the mass flow rate, gravity, and H pump. Alright, so it can be written as this: P2, P1, P1 rho G. Okay, so we can try to solve this. Mass flow rate Okay, we don't have the mass for it. And the mass for it is given, can be given by rho volumetric flow rate. Okay, and G P2 minus P1 rho G. Okay, now we place in the value. So rho is 1000 kilogram over meter cube. V, the volumetric flow rate, is given as 0.05 meter cube over second. Okay, gravity 9.81 meter over second square. P2 is 300,000 Pascal minus 100,000 Pascal. Okay, 100,000 Pascal. Alright, over rho 1000, and gravity is 9.81. Okay, so if we try to find the value of the calculation, what do we get? Let me just calculate using calculator. So certain things can be cancelled out. So for example, this 1000, the rho can be cancelled out. Okay, and the G can also be cancelled out. Right, so we simplify our calculation. So it's 10,000 watt. Okay, so it's 10 kilowatt. Alright, then you want to find the efficiency of the pump. Right, so before you do that, we need to know how much. Okay, we want to know how much energy from the 15,000 kilowatt electricity are being converted to the shaft work. Okay, so we need to calculate the shaft work power of the shaft, power that received by the shaft. So we take efficiency of the motor, multiply with the electricity, the energy. Okay, so here we have 0.9 multiply with 15,000 watt. So we should get 0.9 multiply 15,000 kilowatt, we get 13.5 kilowatt. Okay, we get 13.5 kilowatt. So from there, we should be able to calculate the efficiency of the pump. So the efficiency of the pump, let me see. Okay, the efficiency of the pump is given by the shaft work. Okay, being then at the top we should have the energy that absorbed, okay, by the water. So here the pump. Alright, so what do we have here? We have 10 kilowatt divided by 13.5 kilowatt times 0.5 kilowatt. What we have 10 with 13.5, 0.7441. Okay, so that's the efficiency, the mechanical efficiency of the pump. Alright, so now we look into the question B. Okay, determine the temperature rise. So why do we have temperature rise? So temperature rise is can be due to two reasons. One, if we heat up the water. So in this case, do we heat up the water? No, we don't heat up the water. Second, due to unwanted heat rise caused by friction. So in this case, definitely there's a loss of energy. Okay, the loss of energy, which most likely lost in the forms of heat. All right, so you can see that initially we have 15.5 15 kilowatt electricity given to the motor. When the motor pass it to the pump, here we only have 13.5 because of 90% efficiency. Okay, because of 90% efficiency, and then from 13.5, the energy that transfer to water, the water after passing through the pump, it only take up 10 kilowatt. Okay, so there's a loss here from electricity to the shaft. Okay, we lost 10% of 15 kilowatt, and then from 13 point from the shaft to the water, we lost another portion of energy. How much is lost? About 26%. Okay, about 26% was lost. Okay, so this 26% loss is lost in the forms of heat. Okay, so the heat will be means that the heat will be taken up by the water. So here, how much is the loss? The loss is the difference between 13.5 kilowatt and 10 kilowatt. So we take 13.5 minus 10, you get 3.5 kilowatt. So 3,500 watt should be equal to this formula, the sensible heat transfer. Okay, sensible heat transfer. Alright, so we know the mass flow rate. This is a mass flow rate. This is if you look into the example, it's a sensible heat. Okay, sensible heat coefficient. Alright, sensible heat of water. So C is a sensible heat of water. Right, so you have a mass flow rate is given by rho volumetric flow rate. Okay, C, difference of temperature. So difference of temperature, you could say that this difference of temperature is actually referring to the rise of temperature in the water. Alright, so rho is 1000 kilogram. Okay, volumetric flow rate 0.05 meter cube second, and the C is 4.18 multiply 10 to the power 3 joule per kilogram per degree Celsius. Okay, and then you have a change of temperature. So we want to calculate the change of temperature. In this case, how much could it be? So 3,500 divided by 1,000 divided by 0.05 divided by 4.18 divided by 10 to the power 3. So you get around 0.01675 5, okay, degrees Celsius. Alright, so that's how we calculate for the rise of temperature, okay, in the water due to friction loss. Okay, here is an example of hydroelectric power generation from a dam. So you can see that this example we have gone through before, but this time we look into it again by with a full energy equation. Okay, so you can compare point 1 to point 2. So the water flow from point 1 through a turbine and then reaches point 2. All right, so we write this energy equation with pump, H turbine, and head loss. So we can say that pressure at point 1 and point 2, they are at atmospheric pressure. So P1 equals to P2, so they can be cancelled out. Alright, and then V1 and V2, velocity at point 1, velocity at point 2 are relatively near 0, and they are relatively equal to one another. So they are equal to one another, the velocity, and also near 0. So they can be cancelled out because they are actually, why they are near to 0? Because they are at the reservoir. So the water level at the reservoir does not move that much. Okay, so that's why the velocity at point 1 and point 2 are near to 0, and they are equal and near to 0. That's why they can be cancelled out. Alright, and then here we don't have pump, we only have turbine. Then of course we have some loss. Okay, and then the elevation Z1, if we can assume Z1 as an elevation above, some distance above Z2. So we know if we take Z2 as a reference point, then Z2 can be set as 0. So we know that Z1 minus Z2 would give us 120 meter. Okay, so now we can simplify this equation into H turbine equal to Z1 minus ZL. ZL is the head loss. Okay, so there's some head loss flowing through the system. Okay, for the water flowing through the system, the head loss in the pipe, head loss in the turbine. Alright, so we can calculate the H turbine in meter. Okay, so once you calculate the H turbine, you can multiply this H turbine with the mass flow rate and gravity. So you can turn this whole thing into watts. Okay, so this W turbine is basically the amount of water, the amount of energy lost from the water to the turbine, or in other words, you can say that the amount of energy absorbed by the turbine from the water. Okay, so you get W turbine. So if you know the efficiency, the efficiency of the combined generator and turbine, then you can use this equation where you use the efficiency of turbine generator multiply with the amount of energy energy extracted by the turbine, and then you multiply these two, then you get the electrical energy generated. Okay, so remember that the energy extracted by the turbine from the water, it transfer to the shaft work, and then from the shaft work it transfer to the grid through the generator. So there are some efficiency of the energy conversion from the water to the shaft. Okay, so there are some efficiency by the turbine, and also there are some efficiency by the generator, which convert the shaft work to the electrical energy. So these two combined, generator and turbine combined, give us this efficiency turbine generator, which is 80% of efficiency. Alright, okay, here this example show fan selection for air cooling of a computer. Alright, so we can compare point 3 and 4, and also compare point 1 and 2. So let us start with comparing point 3 and 4. So this fan spinning and force the air to move through a casing. Okay, alright, so this energy equation, you see that they already cancel out the elevation because it's the same elevation. It also cancel out the velocity because the velocity before and after is more or less equal. And then you have this uh, the, the the work, okay, the work done by the fan, okay, providing energy into the fluid, into the fluid, and then you have some kind of loss because the energy loss due to friction. All right, and then you have this pressure difference. All right, so if you take this W fan minus E mechanical loss, you get this W fan comma U equals to mass flow rate given by the pressure difference P4 minus P3 divided by rho. Alright, so in the exact form, this is given by this equation. Alright, and then if you compare point 1 and point 2, so if you write the energy equation out, then you can see that pressure 1, pressure 2 can be cancelled out because they are almost the same. Elevation cancel out because they are at the same elevation, and at point 1 the air velocity almost 0, so we can put as 0. At point 2 is the air is moving quite fast, so we have some value for V2, and then there's no turbine, so we can cancel out the turbine. So this whole equation can be written as W fan minus this E energy loss due to mechanical loss, okay, so the friction loss equals to W fan. So W fan is given by this M, the mass flow rate, multiplied with alpha 2 V2 square divided by 2. Alright, so these and these are the same thing. Okay, you can see that they are the same thing. Then if we know the efficiency of the fan motor, and then we know how much electricity is provided to the fan, then we can actually calculate the W fan. Okay, so if we can calculate the W fan, therefore we can actually estimate the velocity of the fan if we know the mass flow rate. And then if we can do that, also we can use the same equation to estimate the pressure difference before and after the fan. Alright, and if we know one pressure point, then we can actually estimate the other pressure value. Okay, so if we know the pressure before entering, then we can estimate the pressure after leaving the fan. Okay, after the air leaving the fan, we can also estimate the pressure. Alright, this example shows the pumping water from a lake to a reservoir using a pump. So we have a pump, so we can see that the pump is used to pump the water from a lake to a reservoir. So the reservoir is 25 meters above the lake. Alright, and so we can compare point 1 with point 2. We write out this energy equation. So it's the same as the previous equation that we've been discussing about, but just that a different form. Okay, so you have a pressure, velocity, and elevation, and then you have a pump, you have a turbine, and head loss. Okay, and in this case there's no turbine, so turbine can be cancelled out, and pressure is at atmospheric pressure, so equal pressure cancel out as well. Velocity, this is a reservoir, here also reservoir, so the velocity is near 0, so can be cancelled out as well. And then if you take the Z1 as a reference point, then we know that Z2 is 25 meters above Z1, so Z1 can be cancelled out, we only have Z2. So then we can simplify this equation as a W pump. So we have pump equals to mg Z2, okay, mg Z2, and then plus the head loss of the piping. So, and the head loss of the piping equals to mass flow rate multiplied with gravity multiplied with the head loss of the piping system. Alright, so if we know the energy provided from the pump, then we will know this value. And then if we also know the mass flow rate, and then we can actually estimate the head loss in the pipe. Alright, because we know Z2 is 25 meter, the Z2 is 25 meter above Z1. Alright, so in this case they provide the work done by the pump. So we have a
pump efficiency of 72%, and then the shaft work by the pump is 5 kilowatt. So here you get 3.6 kilowatt, right? So you can put it here, and then you know the mass flow rate, you know the elevation Z2, then you can estimate the HL, the head loss. We can also estimate the pressure difference for the pump, which is given by this equation. So P out minus P in, okay, pressure out minus pressure in equals to the pump power divided by the volumetric flow rate. Okay.